Hello, everybody, and welcome to this sort of webinar or live stream. My name is Gavin Simpson. I am a research scientist at the Institute of Environmental Change and Society at the University of Regina in Canada, in Saskatchewan. And well, thank you for your interest. We'll get started in just a minute. Just setting up a couple of things. Okay, so I'm live streaming today from Treaty 4 lands in Saskatchewan in Canada. These are the territories of the Cree, the Saulteaux, the Dakota, Lakota, Nakota, and also the homeland of the Métis. Today, these lands continue to be shared by the shared territory of many diverse peoples, including me, an expat from Britain. So let's just go through a few logistics for today. The first thing is the slide deck is up at this URL here, this link, and the sources are also available. If you did sort of go to the slide deck within the, I don't know, so within the last half hour, you might have got the slightly older versions of the slides. I've just been tweaking a few things, so just make sure you go and refresh that page. Also, if you just wanted to download a zip of everything from the GitHub repo, if you're not a GitHub user, then there's a link there, gam-webinar-zip, that will allow you to get everything, including the rendered HTML files and what have you. Okay. I've put up a Google Doc up here where you can add some questions. I see that already there are loads of questions in here. We haven't even got started yet. I will do my best to sort of go through these things as I go along, and hopefully some of the things that you are hopefully some of the things that you've asked in the questions then will actually get answered during the live stream. Okay, and it will be recorded. Usually the recording will be available at the same URL as the live stream. I just don't know exactly what how YouTube does this, so I'm a bit of a noob when it comes to this live streaming. So I think the original live stream is there, but usually I sort of trim off that first few minutes of the slides, just rotating around before we got going and what have you. So, and it might take a little while for the sort of high definition recording to be available, but it should be available at the same URL that you're watching this from now. Okay. So I mentioned this before, but I'm doing these webinars for free, and I understand, and I'm very much aware of the fact that these are very difficult times for lots of people around the world with the COVID-19 pandemic. Especially so, I mean, our students are in a difficult boat, and because that we aren't able to do any fundraising activities and haven't been able to do any fundraising activities since lockdown in March. Then our emergency fund is starting to run very low. And so if you are financially able to do so just at the moment, I would really appreciate it if you could make a donation to the University of Regina's Student Emergency Fund. And there's a link up here. And if you want to do that and you can't remember the link, then the link is also up at the Git page, which is gam-webinar-git. Okay, this URL up here under sources. So I'd really appreciate that if you can. Of course, there's no obligation to, and no worries. I know that a lot of people are suffering at the moment financially, so no worries if you can't. Okay, thank you very much. Right, so let's get going. What are we going to do? So today I'm going to talk a little bit about GAMs, what they are, and then how we fit them with mgcv. This is supposed to be kind of like an intro thing, and so I'm not going to go into sort of massive detail about all of the options in mgcv. It's a really complex package in terms of, you can get started very simply, but there are lots of bells and whistles and cool things you can do, but they require a bit more in-depth explanations. We just don't have time for that today. So I'll show you how to fit GAMs with mgcv and explain how they're working. I'll then take you through a bit of model checking and model diagnostics, and then we'll have a look at some examples towards the end, which one of them is a bit more complicated, and to illustrate the sort of power that you can do without getting actually that complex of a model. The actual data set's quite easy to understand, but I want to illustrate some sort of slightly more advanced features there. So I might not get round to covering exactly what you were asking, but I will try to pick things up in the questions if you have them. Okay, and so if you have questions, put them in the Google Doc. Okay. Okay, so let's get going. Okay. Here's a motivating example. I think most people should be reasonably familiar with this. It's the one of, there are several of these, but it's an estimate of the Northern Hemisphere temperature time series from about 1850 through to, I want to say this is 2016, the last time I pulled these data. Or rather, that was what was available when I pulled them the other day. And what these are the sort of medians of an ensemble run from their climate models, from their fitting procedure for where they take the temperature data for the Northern Hemisphere, and then they sort of interpolate that to the whole of the Northern Hemisphere to account for the lack of observations in some parts of the world. And then it's been anomalized. That's why some of the temperature values here are below 0. Okay. So, but we can see this clearly rapid rise. And the question would be, well, how would you model these kinds of, this kind of time series? We could put a straight line through these data, but that's not going to do a great job of describing the fact that there has been nonlinear change in temperature over the last sort of couple hundred years. So, I mean, traditionally what we would have done is just stick a straight line through these things, and this is how we might write out a linear model. So at the top here, we're just saying that our observations yi are distributed Gaussian or normally distributed. Each of the observations has some mean, okay? And then there is some common variance. Okay, so there's constant variance. Each observation has the same variation around the mean for each observation. Okay, and then we estimate the mean as some linear combination of our input variables. Okay, so here I'm just showing that this is the model intercept, beta 0, the constant term, but then there are some linear combinations, some effect of x1, some effect of x2, and depending on the values of these covariates, x1, x2, and so on, depending on the values of those covariates at each observation, then we get a different estimate of the mean. Okay? So if we change the x's, we get a different estimate of the mean. This goes in here, and then so our observations are then normally distributed given these values. Okay. So we make some assumptions here. We make assumptions that a key one really is that this thing is linear. And I will show you in a moment how we can generalize this so that it isn't actually linear. You can fit polynomials, but that doesn't actually help us with this problem either. But it's linear in its parameters. Okay, there's no sort of weird things going on in here in terms of the parameters being up as powers. We make an assumption that the conditional on the values of the covariates in the model, that our observations then are normally distributed, then mean 0 with some variance. This is essentially saying something about the residuals in this case, right? So essentially all of the mean information is contained in the values of the covariates in our model. Okay, and this implies then that all the observations have the same variance, because this is constant here, this thing. There's no subscript I on sigma square, so they have the same variance, and that our observations, given the model, given the values of our covariates, are then independent. So it doesn't really matter if the observations are not independent when we just observe them like a time series, as long as we model that dependency include that in our model, then given that model, then our observations are hopefully independent. Okay. When we're thinking about GAMs and what they solve, they really only change the assumption, they modify the first assumption. They just say that we can, rather than having things that are linear in these sort of parameters or these linear functions, there's just a straight line effects, linear effects, that we can actually have some sort of smooth arbitrary effects that we're going to estimate from the data. And we can relax the assumptions about the normality assumption here, this thing that we're saying the observations are normality. We can relax that if we assume, if we're going to fit a GAM, a generalized additive model, in the same way that we would with a GLM. So if we're, why do we need anything more complex than that linear model? Well, this is not linear, okay? This clearly isn't linear. There's perhaps some, if you're just eyeballing this, which, you have to be careful about, there's perhaps some sort of slight decline here. We have some rise, another decline here, sort of in the 60s, 70s. And then we have this sort of rapid, this is almost linear, it looks here, increase post sort of 1975. Right? Now you couldn't fit that with a single linear model. You might have to put piecewise linear functions in there or do something else fancy. So we might actually want a regression model that could learn what or learn from the data what the shape of that trend is given this sample of observations. So to try and make an estimate of what that underlying trend is. So we could do, I said we could fit nonlinear models with the model I just described, with that linear model. That's just by using polynomials, so x plus x squared plus x cubed and things like that. And we can actually get a pretty good fit to the data if we start to use quite high order functions. So this is the linear fit in here in the dark orange. This doesn't fit the data at all well. It kind of overestimates the rate of change in temperatures for most of the time series, but massively underestimates the rate of change that we've seen in the last 50 years or so. Okay. We do better if we start to make these things sort of higher order, and we get a really good fit if we have 8 or 15 terms in our model. But we can see we actually start to get some problems at the ends here. Yeah, you see here that there's oscillating around wildly trying to fit these values. Okay, so this model, even though it's fitting quite well in the middle, perhaps isn't doing a very good job at the ends. And if you're interested in those end periods, then polynomials perhaps aren't a good option here. So we can keep on adding ever more powers to x to our model. We have no model selection. Where do we stop adding these things? So we'd have to do sort of some kind of model selection procedure that then potentially can bias our inference that we do, the p-values and all the rest of it. But also we have this Runge phenomenon, this thing that I mentioned, where you have these oscillations at the edge. And it actually means that just by adding more and more powers of x to our model doesn't always improve the accuracy, and it can actually make the model do very weird things at the ends of the interval that we're trying to fit our polynomials over. So GAMs do offer a solution to this. They offer a solution to the having to decide which order of polynomial we might want to fit. They offer a solution to that oscillation, that Runge phenomenon, where the polynomials do weird things at the ends of the interval. That's what we're going to cover today, is how do GAMs do that, and then see how we actually fit them using the mgcv software. So the data set that I was using there, if you just want to explain some of this so as we go along, things are a little bit familiar. I'm not expecting you to be sitting in our studio and trying to crank this code out. If you do have the GitHub repo down, then you should have an R script that has all of this in. And there's also an RMD file, but that's the stuff for the slides. So you get all of the code chunks are buried in there if you want to see them. The R script is probably the easiest thing if you want to sort of run the code as we go along. So download these data. They're as typical as scientists. They're in sort of, I guess from the old Fortran days and whatever, they're in these sort of just delimited text formats. Often many of these data, although there are some other formats available, we have to read these things in. And so what I'm showing here is how we can read in the data using the readr package and then do a little bit of processing using dplyr. So we can read the data in from a URL. It's space delimited. All the columns are numeric. There are no column names. You have to look at the help for the file to work out what everything is. And so if you were to follow this link here, you'd find information about what's actually stored in here. But we're only really interested in those first two columns of the data set because they contain the year information and the temperature information. Okay? So that's what we've been working with just for this simple example. Okay? So our data ends up looking like this. Here I've got it as a tibble, just a sort of fancy data frame. But you could have this as just an ordinary data frame. And in fact, mgcv was sort of developed well before all of the tidyverse and whatever came about. So it just works just fine with data frames, but it also works just fine with these tibbles as well. And I find them easier to work with for plotting and things later. Okay. Okay. So then to fit our GAM to our data, we need to load the mgcv package, which I'm doing here. Okay. And then if you've ever fitted a model using like LM or GLM, then we have the name of the function, which is just helpfully GAM here. We have our response variable, which is temperature. That's the thing we're trying to model. And then tilde. And then rather than just including the name of the variable, so I could have just included year here, we wrap them in a special function s. And you'll see actually there are a couple more functions that we can use later for interactions. But here, if you just got a single covariate and you want to get a smooth function of that, then you can just wrap it in this s function, and then mgcv will work out how to turn that into a smoother. Okay. And we tell it where the data are, and then throughout we want to be using this kind of smoothness selection, and we'll talk about what smoothness selection is, but for now just make sure you're fitting GAMs, you remember to put method equals reml, and we'll talk about what that is in a little while. Okay. So you do that. It takes less than a second to do this model, and we look at the summary. We get some summary. Now this output should look relatively similar to the output that you might get from a linear model or from a generalized linear model output. It tells us what the family was. Well, we didn't specify that, so we're just essentially fitting a smooth sort of additive model here with a normal or Gaussian response and an identity link function. If you don't know what those are, don't worry about that so much at the moment, but that's just because of the GLM element here. And then it tells us what model we fitted, so we have this simple formula. Then we get the parametric coefficient. So this model is semi-parametric. We have parametric terms, which is the model constant term with the intercept. And then we also have some information about the smooth terms. So this is our smooth of year. It says it used about 7.8 degrees of freedom. These are the effective degrees of freedom. So this is a measure of the complexity of the model. And then we get some test here of the null hypothesis here, which is the function is just a flat line, that there's no effect, just a flat effect. So that's the equivalent of testing the null hypothesis that the coefficient is 0 in a linear model. So we see here this is sort of highly unlikely that you would have got an effect like this if the true effect was a flat function. Okay? And then we get some summary here that we explain some R squared and deviance explain measures and what have you, which are perhaps of lesser importance just now. So it's pretty simple. All we had to do was just change our model rather than just putting the coefficient names in that we want, or the model terms that we want. We just wrap them in this S function and off we go. And then if we plot this model, and we'll have a look at how we might do some of these things later, then this is what you get. Okay? So this GAM has learned from the data that this is what the trend, its estimate of the trend is, given how we set up that model. So a slight decrease, then we see this increase, decrease again, and then it's doing a pretty good job of capturing this more rapid period of increase here. Okay, great, right? That's GAM's work, brilliant, right? So let's go in a little bit more detail now and see what GAMs actually are. You've seen very quickly how they work, but let's explain what was going on there, okay? So hopefully, and this is a slide that I've taken from Noam Ross's GAMs course, GAMs in R course, introductory course, and there's a link to that again at the end. And you can think of there's some continuum from our simple sort of linear models that are really interpretable because you just get a coefficient for each term in the model, right the way up to some fancy black box machine learning tools, deep learning, very deep layered neural networks and so on. Well, GAMs kind of fall somewhere in the middle here. They're a lot more flexible than linear models. They're perhaps not as flexible as these black box machine learning, deep learning tools, but they remain very interpretable because, as you can see, we will be plotting a lot of the functions out of the models. We want to see what those fitted functions look like, and because you can plot them, then I think that's a very intuitive way of seeing what the estimated effects are. It's a bit more difficult to sort of interrogate these black box machine learning methods, although that is an active area of sort of research as to how to explain these models. So GAMs lie somewhere in the middle, okay? And I think they're a happy medium between these two extremes. So another way of writing that model for our linear model that we had earlier, and then we're assuming here that everything is sort of Gaussian at the moment. Then we're saying our observations, there's some constant term, some intercept, plus a linear combination, just some sum of effect multiplied by covariates. This is just the shorthand way of writing that model I had earlier on in the slides. And so all of the GAM is doing is replacing this sum, this linear combination, this sum of linear terms here. It's replacing it with a sum of smooth terms, which we might write as FJ, as SJ. I think later on I've changed my notation and I think I might have FJ in there, so F for a function, okay? Because it doesn't actually have to be a sort of smoother in the sense that we have done for the temperature data. And then the epsilon i's, these are just mean zero residuals, okay? And we're going to assume that our observations are Gaussian for now, right? But these things here, the bits without the epsilons, those are called the linear predictors. Right? So that everything without the epsilon is the linear predictor, and all we've changed in here is the form. We've just created these smooth functions. We haven't specified what those smooth functions should look like or anything like that. All we're doing is just saying we have these smooth functions. And we saw how to fit this. Now you don't have to restrict yourself to a single variable. You could have multiple variables in your model. So here, this is an additive model where we're adding in an extra univariate smooth as some covariate x2, and then we'll look at these in a little bit more detail later, but these are tensor products, so this is the equivalent of an interaction between these two continuous variables. We tell it where our data are. We should be using REML or perhaps maximum marginal likelihood, for fitting, so REML or ML, and then we have our family, and the default was to fit the Gaussian family or normal distribution, but we can fit lots of other distributions as well, and I'll talk about those. Okay, so these are the main things we're going to add to our formulas. We're going to add, usually the terms are univariate, but if we want interactions, we can also use this tensor product thing. And so this is the smooth equivalent of a main effect plus interactions. Okay. So it's actually quite simple to sort of specify these models. We now want to work out how did the GAM function, know that this was the right, that this was the shape of the trend to fit? You know, how did it know that? Right? We didn't tell it anything. We just said, here, use this S function, right? So yeah, what magic is going on behind the scenes here? Well, the main magic is these things, these wiggly things, these, what we're going to call them splines or smooths. I've called them both things so far. But that's really where the magic comes from. It comes from these wiggly little functions that we're going to fit to our data. So here we have our wiggly things. These are splines. And I'm going to show you how we create these things, but you can see that, you know, all these splines that are actually generated in a very simple way can actually create a whole range of different functional forms. So with a single kind of spline basis, a single sort of spline representation, we can create lots of different functions. So we're going to use these splines, these wiggly functions, to allow us to sort of try and estimate the nonlinear patterns in our data, or rather than patterns, I should say, the nonlinear relationships between the covariates and the responses. And so what a spline is it's a basis expansion. Now the polynomial model that we just looked at, that's a polynomial basis expansion too. And so splines are no different to doing this sort of thing in a model where we might have x raised to the power 0, that was equals 1, so that's our constant term, that's our intercept. Then we had x raised to the 1, well that's just our linear term of x. and then we might include x squared, sorry, x cubed, and so on, up to that quite high order term that we were seeing. Well, this is a basis expansion. It's called a polynomial basis expansion. We said we didn't like that one. We're actually going to use a different basis expansion here. We're actually going to use this, a series of different spline kind of basis expansions. So what are splines? Splines are functions that are composed of simpler functions. And those simpler functions are what we call the basis functions. So in the polynomial model here, the basis functions would be the x0, x1, x cubed, x3, and so on. Okay, sorry, x squared, x cubed, right? Those are the actual functions. In our spline models, we're going to have a different set of functions. Okay? And we call those little functions, those are the basis functions, and the whole set of basis functions that we might create is called a basis. And the process of doing this is a basis expansion. Right? So when we model using splines, now we're going to focus on each of our little basis functions. So we're going to, rather than having a basis function for each covariate, just for x1 or x2 or so on, we're going to have a estimated coefficient for each one of our basis functions. So if we look down here, our smoother is just going to be some sum over some basis functions. Here we're saying that we've got capital K basis functions. So it might be 10, it might be 5, it might be 20 basis functions. And for each one of them, we have our basis function that's evaluated at our data. And then we have this coefficient here, this weighting for each of our little basis functions. So this is exactly the same situation that we had here, where in our polynomial model, where we had x to the power 0, x to the power 1, x squared, x cubed, and so on, to give us our polynomial. Each one of these was our little basis function. So we evaluate the value, we get x squared by evaluating x and squaring it, right? And then we estimated a coefficient for each one of these. It's exactly what we're doing in the splines. The main difference now is how we create those little basis functions. So splines, these are formed from basis functions, and this is the sort of form for the basis function, right? Well, one form. Here I'm showing sort of cubic regression spline basis functions, cubic spline basis functions. There are other types, and actually this is not the default, but I think this is the easiest one to sort of understand what's actually going on when we fit the model. All right. So what's happened here is we've had a series of basis functions. We've chosen how many basis functions we want by choosing some locations or knots, which you can see them here. It's where they all sort of cross the 0 line, are all these knots. Okay, so there are so many knots here. I think there's about 10. And so we have a basis function associated with each of those knots. And in this instance, the basis functions are 0 at every knot other than the one that they were defined for. So you can see here this sort of slightly mucky yellow color. It's non-zero at this knot, okay, but it's 0 at each of the others because it oscillates up and down, right? So these basis functions kind of have more of a local feature to them. They are defined, they only take sort of large values over a small range of our covariate x. Unlike polynomials, because polynomials are defined for the whole thing of x, they have some value everywhere, so they affect the fitted model everywhere. That's partly why we get weird things at the ends. But these basis functions here only really take on some value over some limited range of our covariate. And that's actually partly how these things can adapt to the data so well. So that little function that I was showing you earlier that was wiggling around all over the place, we're creating that function, that black line, using those basis functions. And all I'm doing here is just randomly choosing some values for the coefficients for those basis functions. And this is just showing that each one of those weights, it scales those little basis functions around, and then we add them up at each location to give us our estimated spline. Right? Now, I was telling the computer what the values of those coefficients were. What we want to do now is try and estimate those coefficients from the data, and that's how our models, our GAMs, learn from data, by estimating the coefficients to sort of in some way fit our data well. So here I've got a complex nonlinear function. would be very difficult to write down some sort of polynomial that would could explain or could fit to these data, without it getting very complicated at the ends of the series. So over here and over here, it could get shooting off all over the place if we were trying to make it complex enough to fit all of this stuff in here. And the sort of yellowish line that I've fitted through here, that's the model, the known function that I've simulated these data from. And so just added a bit of random noise as we've simulated these things. Okay. So our aim now is, rather than just telling the computer what the coefficients for the basis functions are, we want to estimate them from the data in such a way that we get our smooth curve to go as close to the data as possible. And so we're going to try and recover this dark yellow thing from here. Okay. So to do that, we're going to maximize some log likelihood to get our values of our coefficients. So we're going to maximize the fit of the data given our coefficients. And this is animation here is showing how that works. We're going to find values, weights for these coefficients, such that we move the black line as close as we can to the data without overfitting, right? And that's where the penalized bit comes in, and we'll talk about that in a moment, how we avoid overfitting. But for now, just notice that rather than arbitrarily choosing values of these coefficients to weight the basis functions, we're estimating those coefficients from the data to try and make the fitted spline, the black curve, go as close to the data as possible, right? So that's all the gamma is doing. In fact, if you were to create the spline basis expansion and then just shove this into an LM or a GLM, you would get this fit. All right, you can do this. All a gamma is with these splines, it's really just a GLM or a linear model if we're just fitting a Gaussian response. So there's nothing special here. It's just that we've turned our covariate x, we've turned it into a set of basis functions. So now we're not fitting a function of x, we're fitting lots of these little basis functions, each of which has a coefficient, just in the same way. So once we've created the basis expansion, this is just a linear model or a generalized linear model, right? The only time we need to do anything special is really when we want to avoid overfitting, and this is where this penalization comes in. So how do we avoid overfitting our sample of data? Because we want our model to generalize. We don't want a model that interpolates each of our observations perfectly. We want a model that's going to generalize, because if it was very complicated and fitted our data perfectly, it would do a very bad job perhaps of generalizing to some new data when we try to use our model in some new situation. So we need to think about the complexity of our smooth models. And so one way of thinking about how complex something is when we're talking about smooths is to think about how wiggly that function is. If it's a really wiggly function going all over the place, then it's a really complex function. If it's not very wiggly, if it's in fact smooth, then we're back to something like a straight line, and then it's not very complex at all, right? So this complicated looking equation that I've got on the screen is actually how we measure wiggliness. And then we have another thing. So once we've measured a measure of complexity, which we're going to measure, and I'll explain exactly what wiggliness is in a second. Once we've got that measure of wiggliness, we can then use that to penalize our fit. So if we're going to have a really wiggly model, it must do a really, really good job of fitting the data. We actually want to pay a really high penalty for making something so wiggly. Okay? And so we want to avoid having really complex functions. And we do that. Here we've got the likelihood. So this is a measure of it's the log likelihood. This is a measure of how well we fit the data, given our estimates of the parameters for our basis functions. And then this bit was our penalty. This was just the bit on the right-hand side of this equation. It's one way of writing the wiggliness. Okay, so this is the wiggliness. And how much a penalty we pay for having this for our wiggly function is actually controlled by a parameter called lambda. And we can ignore the half here. That's just to make the thing line up with the Gaussian case, I think. Okay. So this bit here is the wiggliness. This is a measure of the wiggliness expressed in terms of the model coefficients and some matrix X, which we'll talk about. But this is wiggliness. And then lambda just controls how much of a penalty we pay for having that wiggliness. And that, if we take our, so this is the fit, and then we subtract off some amount of the wiggliness, then we get our penalized log likelihood, which is the thing over here. And that's the thing we're going to maximize. So in the end, what we're doing is we're choosing some values of our coefficients plus selecting a value of lambda so that we balance the fit of the data with the complexity, the wiggliness of the model. Right? And there'll be some happy medium, because if we try and have a function that's really, really wiggly, so it interpolates the data, then the wiggliness will be massive. It'll be huge. This thing here will be a really big number. And so no matter what value we're going to pay a big penalty for having something so complex. So actually the penalized likelihood is going to work out to be lower than something that balances, it just sort of goes through the average of the data. Right? So it fits the data reasonably well, but doesn't interpolate it. So this is wiggliness. Let's have a look at what it is. So on this side, okay, we've got some integral, which we're just integrating the function, and we're actually integrating over the squared second derivative. So these two little ticks up here, they are that just indicates that we're looking at the second derivative. Here I called it S before, but I think most of my slides use F for our functions. So we're looking at the squared second derivative, and we're integrating that over the whole range of x that we've observed. This is over the whole range of our covariate. So in a sense, what we're doing, we're just summing up the second derivative that we evaluate everywhere over the function. Right? That's our measure of wiggliness. And so what the second derivative is, first derivative is the slope. So that's the first derivative. The second derivative is the slope of the slope. And so a straight line doesn't actually have a second derivative. Well, it's zero. The second derivative of a straight line is zero. But for those curves that we were measuring, it's actually measuring the curvature or the rate of change in the slope of the line at any point. And so that's going to be, for most of the GAN models that you're going to fit, that is going to be our measure of wiggliness, this second derivative. Now you can change that. You can make it, you can put a penalty on the third derivative or the first derivative or other things, but the default is to use this squared second derivative penalty. Okay, and then conveniently we can write it as a function of the coefficients. So these are our estimated coefficients for our basis functions, and S is called, that's the penalty matrix. So that's just a matrix that we can create from our basis functions that just when multiplied, well, pre and post multiplied by the coefficients, gives us this thing, this wiggliness thing, right? And we might just write this as W to remember that it is wiggliness. And this really is the right word to use. Wiggliness is the right word to use. It gets very confusing because we're not talking about the smoothness. This doesn't measure the smoothness. It's kind of the inverse of the smoothness, right? This is actually a measure of wiggliness. Okay, so a zero wiggly, if there's zero wiggliness, then we're back to a straight line, right? And so we want to penalize this wiggliness to avoid overfitting, because wiggliness is the complexity of this model. And when we saw how do we make the wiggliness matter, how do we include that information about the complexity of the model in our model when we're fitting? Well, we have our log likelihood here. That, as I said, measures the closeness to the data. How well do we recreate the sample of data? Okay. So that's sort of function of those coefficient estimates, the parameter, the betas. Okay. We have wiggliness here. That measures how wiggly or how complex the fitted function is. And then lambda is there just to control how much of a penalty we're going to pay for this wiggliness. So we could actually say, well, we're not going to pay any penalty at all and set lambda to be essentially to be zero. And then this whole thing just goes away on this side. And then we just have the log likelihood. And so now we're just going to fit an unpenalized model, right? But if we allow lambda to go very large, then we're going to pay an increasing cost for the wiggliness. And so the model will tend towards a linear function, right? And if we make lambda infinite, then this will just go back to a linear function, right? And we've just ignored that one, that half term in here, because it's just a constant. It doesn't really make much difference. unless you're actually doing the calculations. Okay. So here what I'm showing then is that Hadley center temperature data, and I'm showing a series of different fits. So here with different lambdas. Okay, so lambda here when lambda's at 10,000, we've already got back to being a straight line. That's the best sort of fit if we want to pay a really large penalty for the wiggliness. This is penalizing very strongly against away from a linear fit. If we relax that a little bit, so here we've got lambda equals 1, we get something that looks a bit like x plus x squared, just sort of some quadratic function. All right, it's not quite, but it's similar to sort of that. You know, it's that simple. And then here we've got an example where we're overfitting, where the lambda is some really small value, and we're starting to not really pay much of a penalty, and so the estimated curve is wiggling all over the place. So this one is overfitted, and these two are underfitting because they're not really capturing much of the features in the data. Right? This one's capturing almost nothing of the data. This model here has lambda, which is just about, it's almost right. I just chose this to be a nice round number. It's not quite the actual value of lambda that we estimated earlier, but it's pretty close. So here we see sort of the general features of it: declining, increasing, a slight decline, and then another increase. Okay, and so the job now, really, we've boiled everything down in our GAM to fitting a model, so estimating some coefficients to maximize the fit of the data, but we then have to find a value for lambda that sort of controls how much penalty we're going to pay for having a really complex wiggly function. So we don't want to have a function like this in the bottom right where we overfit the data, and we also don't want to have something that looks like one of these two at the top where we're not really capturing the fit at all. Okay, and so lambda is this thing called a smoothness parameter, and the thing that makes the GAM function different from the GLM function is that it's choosing lambda. If you just fitted this using GLM or LM, then you would be having essentially an unpenalized model that you're paying no penalty, and so you're just going to estimate whatever functions you can given the basis functions you've estimated. What the GAM function is doing, it allows you to choose or estimate, select the value of lambda. So now we pay a penalty for fitting complex functions, and that's really, for the simple stuff we're going to look at today, that really is the only difference between the GAM function in mgcv and the GLM function that comes with base R. Okay, and just before I go and have a look, we've got a couple more slides just on this, and then I'll have a look at some of the questions. So how do we pick the right wiggliness? Well, this really comes down to that method argument that I mentioned earlier when we were fitting, and I said it should be set to REML or ML, but usually REML. So there are two ways to think about how we might choose or optimize our value of lambda, the smoothness parameters. So the original way, and one of the reasons why mgcv is called mgcv originally, is because it used a thing called generalized cross-validation, and that then is a very predictive mode. We might want to choose lambda to minimize some out-of-sample error. Okay, so i.e. this is a predictive mode, right? Or we can be Bayesian about this and think of lambda as being a prior on our basis coefficients, or a prior on our expected wiggliness or complexity. And it turns out that if you view things from a Bayesian approach, then you should be fitting, that's what you're doing when you're fitting using method equals REML or method equals ML. Okay. If you're doing things in a predictive mode, then you'd be using things like AIC, Mallows CP, or as is currently the default in mgcv, is to use this generalized cross-validation thing. This generalized cross-validation thing basically means that you don't actually have to do the cross-validation, i.e. repeatedly fitting the model to subsets of your data and then predicting for the bits you left out. The generalized bit just tries to estimate what that cross-validation error would be, right? So the first three, AIC, Mallows CP, and GCV, they all are from this predictive way, just trying to find a value of lambda that gives you the best out-of-sample prediction. But what we advocate for sort of stability and various other reasons is to sort of be a bit more Bayesian about things and use this method equals REML. And one of the reasons, I mean, it's not just about being Bayesian because we can be Bayesian and be all sort of fancy. What has been found, and this is a figure taken from one of Simon Wood's papers. I think it's the 2011 paper on REML smoothness selection. This is the function that they're trying to fit. And then here we've got, this is log lambda, so this is lambda but on the log scale. So this is our smoothness parameter. And what is happening here is that if you vary the value of lambda, this is the log of the GCV criterion. This was the default that mgcv was using to fit the models. And so this is the function that you're trying to optimize on. So you're trying to walk down this surface and find the minimum here, okay? But you can see that this GCV function has actually become pretty flat in this instance. And so depending on which sort of sample of data, because you can keep sampling data, then you can actually choose values of lambda that were close to -10 or close to -5. And this actually represents quite a large difference in the wiggliness of these different functions. And so it was realized that just depending on what sample you had, then the GCV criterion might undersmooth or oversmooth depending on the setting, right? And so what was shown in this paper by Simon Wood in 2011, but had been shown elsewhere as well, is that we have this, if we use the REML criterion for the REML method for smoothness selection, then there's a more pronounced minimum in the examples that were done here. And so now we get much less variation in the estimate of the smoothness parameter when we repeatedly sample from the true model, right? So this is much better, okay? In terms of choosing our estimates for lambda, but it also has some nice benefits of viewing everything in a Bayesian way, which we'll come back to later. Okay, couple more slides now just on, I said basically everything comes down to choosing lambda. It's not quite the only thing that we have to really do. The user does have some control. So apart from just putting S as the function into our formula, you do actually have to do something else, and we ignored that when we fitted our models earlier. But we need to set the basis complexity, or the size of that basis. How many basis functions do we want to use? And that's going to be controlled by some parameter k. So you can think of this as being the maximum wiggliness that we want to fit, that we want to allow. And another way of thinking about it is that this is the maximum wiggliness that you expect your functions to have, plus a little bit, right? Because you might have underestimated it slightly. But what you're doing when you're setting k is you're putting some upper limit on the wiggliness, and you're saying, I don't expect the relationship between x and my covariate to be any more complex than functions that can be represented by a basis of this size, right? So you're really this is an upper limit on the complexity of the model that you want to fit. When we do our fitting, so k sort of sets the degrees of freedom, the maximum degrees of freedom of the model. But once we've done our fitting and done the penalization, we know we'll have smooths that use fewer degrees of freedom, and we call those effective degrees of freedom. So EDF will sort of be less than, because the penalty will have shrunk those coefficients and stopped us using the full range of that basis, because that might have allowed us to overfit. So really what we're saying here is that k, and it's something that you actually can set in that function s, k must be large enough to cover the expected wiggliness of your functions, and you set it for each of the functions in the model if you want. K must be large enough so that it can capture the true function or something that's sort of a close approximation to the true function. And then we let the smoothness penalty, or penalties if we've got more than one smooth, we let those penalties do the rest of the work. So large enough, what we mean by that, the space of functions that can be represented by the basis, we hope it includes the true function or some close approximation to that true function. And that's what we try and do. Now, it can be quite difficult to, especially if you're new to GAMS, to sort of guess what k might be given the functions. But actually, I think usually when you start playing around with this, you'll realize that if you have k of 10 or 15, you can get some very complex functions out there. And unless you're doing things like space or time, smooths of space or time, it's unlikely, or some very special situations, it's unlikely that you would need k to be very large if you're just looking at the smooth effect of a covariate on the response. There are some situations where you do need k to be large, but usually you don't need k. You'll get a handle on how big k should be just because you don't expect there to be very complex functions. But for doing things like time series modeling and spatial modeling and what have you, then sometimes k actually might need to be a bit larger, a lot larger than you would expect to capture nonlinear patterns in the data. Okay. Now, the only real cost of making k big and setting k to be almost as large as the number of observations that you have in your data is that k comes, the bigger the basis, the greater the computational cost, right? And if we have a lot, if you don't need all those basis functions, the true function that you're trying to estimate is much less complex than that, then you're just carrying around all these extra basis functions for no reason. That adds increased computational cost. And so in mgcv, the default values are set to sort of give you a reasonable amount of wiggliness, but they're essentially arbitrary. Simon Wood, who wrote mgcv, doesn't know, and GAM itself doesn't know what an appropriate value of k should be for your smooth functions. It just sets up it has to give some number just to make them work, to make it easy to work. But it is something that you can choose. And so really when it boils down to it, you're not choosing lambda. The software is going to choose lambda, the smoothness parameters, right? But you are in charge of setting this maximum allowed wiggliness. And so k really is the only thing that you need to specify in those smooths to choose. Or you can leave them at the defaults and then check. And we'll use gam.check to have a look at that shortly. Okay, so let's have a quick summary and I'll go and have a look at some of the questions. So GAMs give us a framework to model flexible nonlinear relationships in data. You don't have to specify that it is a polynomial, an 8th order polynomial or a 7th order polynomial. We've seen how GAMs use these little functions, these basis functions, to make big functions, these smooths. We've seen how we use a penalty to trade off wiggliness with generality, i.e. how well our model generalizes to new data that we haven't seen when fitting. And then the last point that we just made was that the only real thing that you need to do is to make sure that your smooths can be wiggly enough, that they can potentially capture that true function, i.e. that your basis is rich enough to potentially cover the true function or a close approximation to it. Okay. Right, well, we'll come back to the example in a second. Let's see if there are sort of questions here. We'll come back to some of those. Ba-bum. Ba-bum. Don't think there are loads of questions here about what I've just talked about. Okay, so one question here is asking, so yeah, there is one question here that's asking about this, what I've just, to some extent what I've been talking about. So what is the criteria for selecting the different smoothing parameters? Or the different estimation methods, REML, GCV, and all the rest of it. I think we would say the default to start off would be is to use REML. That's the sort of one that seems to be most robust to violations of a lot of assumptions. And I'm not going to talk about it, but there is an assumption of, you can get these things called concurvity. So you get functions that are highly correlated, but they're non-linearly correlated, and so REML can be a little bit more robust to that. Also, though, what I talked about in the slides about having the GCV function can get flat in some situations and might undersmooth. We don't want to undersmooth. We don't want to oversmooth either, and REML seems to work sort of the best for that. Okay, so that's what we should sort of been doing. Someone's asked here about if we're fitting sort of local pieces of a response to variables. I think you're not. You're not. The question then is, how do you phrase hypotheses about the gamma and the relationships in your predictors? Well, I mean, the underlying it, yeah, there are these little basis functions that affect the fit of the model in small places. But really, what you want to step back. That's the mechanism by which these functions are fitted. You want to step back from that and think about the actual function that you're fitting. So we're saying that there isn't just some linear relationship or some quadratic relationship between x and our response. We're saying that there is some smooth relationship, and we want to try and estimate that smooth relationship. So one way of thinking about it is, if we're trying to model, say, what the temperature is, and we can't, in that record that I showed you, there's no seasonality because it's anomalies. But if we had temperature data measured throughout the year, we might want to say, well, okay, how does temperature vary? We could, through the year, we could use sort of sine and cosine functions to get something that goes up and down throughout the year. And that has been done. But those sine and cosine functions are symmetric. They assume that the rising limb is the same as the falling limb, unless you make the model more complex to have asymmetry. And whereas the GAM version would just say, okay, I can have some smooth function. It doesn't have to be symmetric. So you're not making any formal statements about the exact shape. You're just saying that there is a smooth, that as you change x, the response varies smoothly. Okay. I think most of the other questions I'm going to get. So any advice on how to choose k? We'll talk about a sort of an ad hoc way of doing this. If you don't have any prior information for choosing k, then really what you do is maybe go with the defaults and see what happens. And then as we'll see in a minute, you can use this function gam.check to look and sort of see whether you had a large enough basis, right? And I'll talk a little bit about what gam.check does. So yeah, someone's asking, is it possible to plot a categorical variable with GAMs? So you can't do a smooth function of a categorical variable, but you can include categorical variables in the models, and you just add them as you would any other variable to the formula. You just don't wrap them in the S function. Okay? There are some exceptions to that. For example, if you want to have random effects, you want random intercepts, then rather than fixed effects, then you can put them in as a random effect, and then you would use the S function, but I'll talk about that in a minute. So I think I'm going to talk about most of these things in a minute. Okay. So let's go and have a look at an example now. So this is an example that's taken from the GAM-Air package, which is the package of data sets really that comes with Simon Wood's book, an introduction with Generalized Additive Models, an introduction with R. And so what we have here is there's actually a series of different birds in here. I think there's the crest lark and the linnet, but we have this data set that we load in from the package, and then we're going to do some transformations. And so all we're doing here is just turning the crest lark and the linnet into a factor so that we can just choose is 0 or 1. That's just because we're going to fit a presence absence sort of model here. Was the species present or absent? That's 0 and 1. There are some NAs as well in here, which are where the data are missing. And we do that for these two species, although we're not going to fit the linnet data. And then we're going to take the X and Y. The X and Y coordinates are in meters, and they're in the national grid of Portugal. But these are big numbers. You can see here they're in the hundreds of thousands or even more, right? And these are big numbers, and we don't want to be trying to fit these such big numbers in the model. So we're just going to divide them by 1,000, and that just gets rid of all of these zeros at the ends. Okay, it's just rescaling. It just helps with the sort of fitting. Everything's sort of on a more reasonable scale. And so this is the sort of data that we're going to work with. So we're going to use these sort of easting and northing and then we're going to, our data set that we have is this crest-lark data set, and so it's now a factor, it's a 0 or a 1. Okay. So what we're going to do here is we're going to fit our model. Crest-lark is the response variable, and because if you've ever fitted a GLM, this 0, 1 factor, that will allow us to fit a binomial GLM, so like a logistic regression kind of model, where the 0, the first level of the factor is the sort of, or rather every other level of the factor apart from the first one is the positive, i.e. that we had a positive effect, and then the reference level is the zeros where it was absent. So we're going to model the presence-absence of this bird at each of these grid squares using a two-dimensional smoother. Here we're using the Easting and Northing, and then here, because there's potential for this to be quite sort of complex in terms of trying to model these small pockets of the data where the species is actually present, okay, given that there's lots of places where the species was not observed, right? We're going to use quite a high degree of K. And this is essentially trial and error. I think this is a balance here. We've got quite a lot of observations, but we don't want to have a really high K because that makes the model more difficult to fit. We tell it where to get the data from. We tell it what kind of model. So we're saying that the response is distributed, conditionally distributed binomial. So there's 0, 1 essentially in this case. And then it's actually Bernoulli, but that's a special case of the binomial. And then we're going to do smoothness selection using REML. What this SEN, normally we've seen an S of just one function. Well, we can fit bivariate or even higher order smooths by including extra covariates inside the S function. Okay. This creates what's known as an isotropic thin plate spline. This basically means that the smoothness in the direction of E is the same as the smoothness in the direction of N. And it basically means that we can have a single smoothness parameter even though we've got this two-dimensional smoother. All right? But it's a bivariate thin plate spline. We'll talk a little bit more about these interactions later. And then we have K, which sets up the basis dimension. So that's our upper limit on the effective degrees of freedom, so the complexity of our model. And then, as I said, we're estimating using REML. So this is the output, and hopefully you can see this on the screen in the slides. Sometimes the output gets quite large, so difficult to cram it all in sometimes with Markdown. But here we had this is our intercept, so our parametric terms. There was only one of those. There was only the intercept here. Remember, you don't specify the intercept in R's model notation. But there is an intercept in here. Okay, and then here we have our single smooth term, our bivariate smooth, and it's now using about 75 degrees of freedom. So the penalty, as said, we started off with about 100. It's actually a couple less than that, I think. 98 basis functions, and then the penalty has actually shrunk that back down to just using about the equivalent of 74 basis functions. And then, I mean, it doesn't really matter here. The fact that this is so far away from 0, it doesn't really matter that whether this p-value is less than some threshold or not. There's clearly we've estimated a function that is not a flat function, right? Okay. We don't do a great job, but this is 0, 1 data, so we explain about 26% of the deviance in here. Okay. Now, doing the model checking using this GAM, we'll have a look at so that's the output. We'll look at more outputs from GAMs in a minute. Doing the model checking for binary data is actually a bit of a pain. No matter what you do, the residuals in the diagnostic plots are going to look really weird. And so another thing that we might do is rather than fit our model to the individual observations, these much smaller grid squares, then there's a larger grid square, I forget exactly how much larger it is, that they call the quadricular, and that we could just aggregate everything to that quadricular and see how many times in each of the little grid squares in each quadricular did we find the species. So now we have binomial counts. We don't have 0 and 1, we have 0, 1, 2, 3, 4 out of some total possible. And this is what I'm doing here. And I'm not going to go through the code, but basically I'm having to undo what I was doing to set them not as factors anymore, but as 0 1s. And now we're going to count up how many of the, so rather these are indicator variables that indicate which of those big grid squares we're in, and then we're calculating how many of the little grid squares in each of the big grid squares had an observation. So we're summing up all the little observations, and then we're just dividing that by the size, so the number of grid squares, and then we refit our model. So this is now binomial counts. We just aggregated everything at the grid square level, and if this sort of works okay, then it's perhaps more likely, if this model is very similar to the model we had before, then it's likely that this that our original model was also a pretty good one. It fitted the data well. And there are other options for doing model checking with binary data, but this is just a sort of a quickish way to do it with the default, the sort of things that are available in mgcv. You can use the Dharma package, for example, to sort of do randomized quantile residuals and things like that would help to try and solve some of the problems of testing with checking binomial models. So if we do this, if we fit that model with the aggregations, then the residuals don't look too bad. You still get these bands in here, but these are the sorts of things you see all the time in count models. That's because you can only have these integers, 0, 1, 2, 3, and so on. Okay. So those are just the integer representation. And then actually what I'm doing here, I've changed it from being binomial to quasi-binomial, just to see if the model is sort of the data are over dispersed relative to the model. And actually, if you were to look at the summary for this model, you would see that the estimated dispersion parameter phi is 2.32, and it's in the binomial model it should be 1. That's what we assume, it's 1. And because it's larger than 1, it suggests that there is a bit of over dispersion here, right? So the model doesn't look too bad, and it suggests that our original model was okay. Well, we've seen how we can fit a two-dimensional smooth, how we set k, and you have to just set that, and we'll look at how we then can test whether k is large enough in a minute and see whether we needed to set k even higher. It doesn't look like it in here because the penalty is actually shrunk, but that's not a good enough justification to say that k was large enough. Let's say k should actually have been 150. Then if you start off with a set of functions that can be represented using 100 basis functions, but the true function can be represented only if you have 100, well, if you only have 100, if you have 150 basis functions, then this is going to move away. This model is going to move away from that to where that true function is, because it can't even represent the true function. So even with a large number here and the EDF being shrunk, even then you might want to be a bit careful about assuming that 100 was enough. Right, so let's just have a look at a few bit details of things that are in mgcv before we start looking at doing model diagnostics more and model selection. So I've just shown you at the last few slides the default, which are these thin plate splines. These are low rank thin plate splines. The reason they're the default is that in a thin plate spline you have a knot for every unique value of the data of your covariate X, or in the case of the LARC dataset, the easting and the northing, every unique easting and northing has a knot. So we don't have the problem of choosing how many knots to use and where to put those knots with the thin plate spline. The problem we have with the thin plate spline is that if we have that many knots, then we have a basis function for every unique combination of the input values, which is a lot of basis functions, and we probably don't need that. There is no reason to assume that the functions we want to fit should be that rich, that potentially that complex. And so what Simon Wood came up with in a paper, I think in 2001, is a low rank version. And so it's just a way of taking that really rich thin plate spline basis and doing an eigen decomposition on it, a bit like PCA, and turning it into so that we just take the first k, the first 10, say, or the first 15, or the first 100 basis functions from this rich, large basis. And the idea here is that you concentrate the information in that basis, you concentrate that in the first few eigenvalues, in the first 10 or the first however. So the eigenvalues are ordered from the most information down to the least information, i.e. the most wiggly is the last one, and the first one is the sort of the smooth ones. Okay, or close to being smooth anyway. And you only want to take those first few basis functions, be it 10, 20, 100, leaving all of the others away. And so you fit your model using that. Right? But you don't have to use thin plate splines at all. I mean, they are the default. They have lots of optimal properties in terms of how they sort of fit the theoretical properties, how well they should fit the data. But there are lots of other splines that you can fit. So one that often people have heard of is these cubic splines or cubic regression splines. That's what the CR bit does. Those are quite popular and people fit them. And these ones, if you've got a very big data set, the thin plate splines can be really, it takes a lot of computations just to do the eigen decomposition and create the basis, right? So if you've got a lot of data, you don't want to be wasting it all just creating the basis. So the cubic spline basis is a good alternative there, because you just set k to be what you want, and you get that many basis functions already defined. Okay, although you do have to you could want to then choose where the knots are, but usually you just let mgcv choose where the knots are. But there are lots of other bases that you can types or spline types that you can use, and which one you actually fit is selected by using this argument bs. So if bs equals tp, that's the default, you get the thin plate splines. If you want any of the other splines, then you just change the bs argument to be some, and you have to specify it as a character string like this, okay? And you do that inside each of the S terms. So each different smooth in your model could actually use a different basis. So there are some standard things like cubic splines and p-splines. Then we have these cyclic splines. So if you've got data that varies over a cycle, like from January 1st to December 31st, something like that, you want the ends of the splines to join up. You don't want to have a discontinuity, because January the 1st is almost the same as December 31st. Okay. Then you can use these cyclic. So this is a cyclic cubic spline or a cyclic p-spline. There are other things. Duchamp splines are useful for spatial smoothing, and they're actually a generalization of this thin plate spline. If you've got data on the globe or on a sphere, then you can use splines on the sphere. And then we've got some really fancy things like Markov random fields, which don't really look like a smooth function, but they can be written in the same way. If you want to smooth data over a fixed boundary, then soap film smoothers are cool. You can fit Gaussian processes. We can have smoothers where the wiggliness varies over the function. So it could be entirely flat and then go really complex. Okay, so go flat and then really, really wiggly. And that's an adaptive spline. And then we can have things like random effects or random smooths as well. So there's lots of these different ways of fitting things. We'll have a look at a couple of these as we go along. For the most part, you can stick with the thin plate splines, but knowing that if you've got big data, you might want to go to a cubic regression spline. And there's a whole load of conditional distributions. We've just seen a Gaussian and a binomial and the quasi-binomial family. Well, all of the families that the GLM function can take, the binomial, Poisson, gamma, inverse Gaussian, etc., those are all available within mgcv. But also in a more recent paper by Simon Wood and colleagues, they've extended their models to a much larger range of conditional families. So we can have a negative binomial model where we estimate the overdispersion parameter, or we can have Tweedy models. This is for continuous data where 0 is allowed. We have multivariate normal, multinomial models. So if you've got multivariate responses, you can do those. If you've got beta, so these are continuous proportions. This is a scale t, so it's similar to a Gaussian, but you've got potentially large values out in the tails. So scat is the scale t is a more robust version. So it's not as affected by the outliers in those tails as the Gaussian. Then we've got location scale models where you can fit, here's a Gaussian Gaussian location scale model where you can fit the mean and the variance. This is a zero inflated Poisson where you can fit the zero inflation as using a GAM model and the Poisson part as a GAM model. There's a location scale version of the Tweedy, and then this one's for the gamma. There's a location scale model for the gamma. This is ordered categorical, so like thinking of like categorical responses where I think proportional odds models, and then you've got here a Cox model for survival analysis. So actually these models now are really You can do a lot more than you can do with the GLM function just by switching to use these different formulas, conditional distributions. We'll note that not all of these can be fitted with all of the functions in mgcv. So the GAM function can take all of these, right? But the BAM function, if you've got big data, BAM, and we'll use BAM at the end, then BAM can only use some of these. It can't fit like the location scale models and the Cox pH model and so, yeah. But it can fit things like the SCAT and the beta and so on, right? And then other things like the mixed model versions of these, they can't use any of these things. They can only use the standard families that are available in NLME or in LME4. So, you know, the greatest choice comes with the GAM function. You have a little bit less choice with the BAM function, and then you're back to just the ordinary GLM families if you're going to use GAM or GAM4. All right, so I talked a little bit about this already, but how do we fit interactions? So these are smooth interactions. This is the equivalent of having an interaction between two continuous variables, so x times y in the formula. Well, we've already seen one way that we can do that. We can use bivariate or higher order thin plate splines here using the BS equals TP, the default. So you just put extra, you just add in the covariates, the continuous covariates here, and then it will create the basis for you. Now, the only thing to be aware of here is this is isotropic. There's a single smoothness parameter for this smooth. So it's only really useful for things where x and z and whatever are measured on the same scale. And so that's why we used it in the spatial example. Even there, though, we might think that there might be more variability going north to south in Portugal in terms of things, because that's more of a degrees of latitude than there is going from east to west. It's also sensitive to the scale of x and z. So if you were to fit x and z in the raw coordinates, like the easting and northern coordinates, and then you divide one of them by 100, then the whole smooth could change, right? Just because you've scaled one variable relative to the other. So you have to be a bit careful about these, and really you should only use them for things where they're in the same sorts of units. More general interactions can be done using tensor products though. So we don't have to make this assumption that they're the same smoothness in X and in Y. So the tensor products, what they do is I'm not going to go into too much detail about how they're created, but you can think of it as you've got a marginal basis. You have a basis for X and you've got a basis for Z, and then there's some magic that goes on that just says, well, no, I want these two things to interact. And we create a basis that includes the main effects, so the marginal bits, plus the interaction. And it's done using a thing called a Kronecker product. It just takes the two marginal bases, multiplies them together through this Kronecker product operator, and then you get the interaction that just falls out. It doesn't really matter how you scale x and z, because each marginal basis just adapts to that. And so if you change the scale of one of these, then it doesn't really change the smooth at all. And so this is really useful if you want interactions when the variables are in different units. And so if you've got two things, if you're not thinking about space or space and time, then TE should be the way to go about fitting those sorts of models, right? And TE just means a tensor product of a marginal basis of x and a marginal basis of z. There are actually multiple different ways, and to fit these tensor products or to create them, the default, the original one, is to just use this TE function here. There is an alternative parameterization, which is known as, we use this T2 function. The reason that exists is that the TE function, the most general one, can't be used in things like GAM4 from the GAM4 package or BRMS because of the way you have to represent the random effects in those models. So at the moment, I think the BRMS package might be potentially, I think Paul is looking to change that and make TE usable within BRMS, but at the moment you can't do that. And so there's this alternative formulation that does work really well with and can be used in GAM4 or in BRMS. And so that's this T2 term. Yeah, works the same way. You just give it X and Z and your covariates and so on. And then there is one more. So if you wanted to decompose your model into the main effect of X, the main effect of Z, plus then the pure interaction bit, then you can't do that. You can't break your the tensor products out into this kind of representation if you use the TE or the T2 terms. Essentially, the interaction bit is buried up inside all the little basis functions that you have, including the main effects. So they're all in there, and it just, as far as the model is concerned, it just looks like one smooth function that contains the main effects of the two things plus their interaction all jumbled up. So it's really hard to know if you even need the interaction or not with these two things. So what mgcv offers, and what Simon's implemented, is where you can fit the two main effects, so s of x and s of z, okay, you can fit those, but then you can just have this bit represents just the interaction part, whereas this one includes the main effects and the interaction. TE doesn't, it only includes that interaction part. And this allows you to do a decomposition into the different effects. And we'll see at the end when we do an example, this is quite useful for building up quite complex models where your terms, these x and z's, might end up being included in multiple parts of your model, right? And really it'd be better to include their main effects first and then have these interactions with the other variables, right? For sort of computational reasons. Okay, now that was if we've got two continuous variables. Now, what if we want to have an interaction between a smooth and a factor variable? So let's say we've got, we might be doing sort of male-female kind of things. We might have different colors of flowers and things like that, different levels, different locations, different lakes or different sites. Then you might want a different smooth for each site, for each color, and so or what have you. There are two ways to do that. The first way is to use bi-variable smooths. And what they do is they set up basically an entirely separate smooth function for each level of the factor. So if you've got, say, red, green, and blue, each one of those is going to get its own smooth, and it's going to get its own smoothness parameter. So you might have a really wiggly function fitted or estimated for the red color, but you might have just simple linear or very simple smooths estimated for the other green and blue, for example, right? For the other levels. These things are also centered. So if you're going to do a bi-variable smooth with factors, then they're centered. They don't include the group means. And so you must include the factor as a fixed effect in your model. And that's what I'm showing here. So this might be the formula. So we have our response is just, here is our parametric fixed effect for the factor f. And then we want a smooth of x for each of the levels of f. Right? So you have to include this categorical term here in the model formula. And that's because these smooths are centered. Because otherwise you could, the smooths themselves wouldn't be identifiable, because you could just add some constant value to one smooth and subtract it from something else, from another smooth, and you'd have the same models, and you'd can fit the data equally well. And so we have to center everything to about 0, but then if you center everything about 0, you don't have the different means for the different levels, right? So including the parametric term includes the different levels, group means, okay? And you can think of this a bit more like a sort of a hybrid of a fixed effect with these smooths, because you're interested in estimating a smooth for each one of these specified levels, yeah? If you want to move somewhere that's a bit closer to sort of the random effect idea, and if people know anything about splines and the Bayesian view of splines, they're probably cursing me now, because everything is just a random effect in these GAMs with REML, all right? But these splines, these are much more like random slopes, but they're just smooths now rather than random linear functions. We can do that using a special basis, the FS basis. You get a smooth function for each level of the factor, sorry, that should say, not the function. But they share a common smoothness parameter. So we're saying that all of them are sort of roughly the same sort of wiggliness, but their shapes can change, the shapes can be different, but they just have the same level of wiggliness. And these things are also fully penalized. They're not centered either. So they include the group means, which means you don't need to include f as a parametric term. And so, as I said, these things are much closer to this idea of being a random effect. Yeah? And the way you specify that in the model is you have your response, tilde, and then you use the s function. You have your continuous variable, then your factor variable, and then when you say bs equals fs, That's how you get this special factor smooth thing. Okay, so in this one, you don't need to have f as a parametric effect, but with the bivariables, you do need to have f as a parametric categorical effect. Okay, and I've mentioned this a little bit sort of before just now, but when we're fitting with REML or ML, smooths in the way that they're described in these models using REML smoothness selection and stuff, they're just really fancy random effects. And also the inverse of that is true, that random effects can just be viewed as smooths. There's a kind of duality here, and you can just choose whichever way you want to view them. Do you want to view the smoother as as sort of a mixed effect model, or do you want to see the random effects as just smooths? And this duality means that you can actually fit random effects inside GAM and BAM, these functions, which normally you wouldn't expect to be able to fit mixed effects models, but you can do that quite easily without needing to go to these more complex generalized additive mixed modeling functions, GAM, which comes with mgcv, or this GAM4 function, which comes with the GAM4 package. This one is fitted using NLME. This one is fitted using LME4. Yeah. And so if you know anything about mixed models, these two models here are actually the same, right? Here we're fitting a linear mixed effects model where we just have an overall intercept, and then this is the rails data, and then we have a random effect, a random intercept for each rail. Okay. Well, the way we do that in this model, if we want to include a random intercept for each rail, we have our response, tilde, and then we just use the S function again. We give it our factor variable rail, but then we have to tell it that this is a random effect basis. And so this doesn't actually set things up using the usual wiggliness penalty. It does something slightly different, but it can still be represented in the same way. And so these are random intercepts. And those two models are equivalent up to the algorithmic implementations, the way that they're implemented in the computer. But mathematically, these two models work out to be exactly the same. So if you do have simple random effects, then you can include them in the GAM function. And then when you do that, all of these families become available to you. Normally, if you wanted to try and do this thing, you might have to use some very specific mixed effects modeling software to try and get these more complex families. But if you do have simple random effects, you can use them with GAM and include random effects in your model. Okay. So just another note on that. These random effects are not as computationally efficient as NLME or LME4 are for fitting these models. And essentially what you're doing is you're taking your GAM representation and given some estimate of the random effect variances, and you try and you just kind of estimate that model that way using the smoothness parameters become the variance parameters or equivalent to that. And so you estimate this thing. But it's asking quite a lot of NLME or LME4 to do that fitting. They're quite complex models. But if you've got very complex random effects, or you've got random effects with many levels, then GAM gets really slow. And so you might need to use these more, these functions that are going to use NLME or the LME4 packages. It's going to use those to do the fitting, because those packages have got special algorithms that are designed for fitting complex random effect terms in their models. So they are explicitly designed to fit random effects. They don't fit smooths, all right, but they do fit random effects, and so they have algorithms tuned to that. GAM, the GAM function and the BAM function in mgcv, they were designed and have algorithms that are tuned for fitting smoothers, like smooth functions. Okay, now they work quite well. They're reasonably efficient if you have simple random effects or a few levels, but they're not designed for fitting complex random effects. So if you do need complex random effects, use one of these two functions. And I would recommend, if you need to use, if you're trying to fit generalized additive mixed models, so you're not fitting Gaussian families anymore, not fitting normal models, then you should use the GAM4 function, because that's it uses a much better algorithm for fitting these generalized additive mixed models or generalized linear mixed models. Okay, and GAM4 can make use of those fancier algorithms. Okay, we'll just check the the questions, if there's any questions in here. Okay, so someone say one question here: if n is low, i.e. less than 10, Does that sort of, is there any relationship between that n and the k? Well, if you've got fewer than 10 observations, then GAMs are probably not the model for you. You can do it, you'd have to set k pretty low, okay? But you're asking quite a lot. So you'd have to set k to be sort of no more than 5 or 6 or what have you. I mean, the penalty will still work, but it's just going to be quite uncertain. And there's going to be a lot of uncertainty in that smoothness parameter estimate as well. And so really, if you've got fewer than sort of 10 observations, you're not really in GAMs are not really the best model for that. Someone's asking, why is a GAM a better option than a GLM or a GLZ? Well, so I think what you mean by a GLM is not what I mean by a GLM. So I think you just mean a linear model or a generalized linear model. So I think the key thing is why assume that the effects are linear? In the case of a generalized linear model, they're linear on the length scale, right? But why assume that the effects are linear? The advantage of the GAM is that we don't have to assume that they're linear. But if the linear model is appropriate, the penalty can actually shrink everything back to being a linear model. Okay. So I'm going to look at a couple more questions. So I think the question is, people don't like jumping between different packages when fitting regression models. Is there any issues with fitting linear models, GLMs or GLMMs in MGCV? No, not at all. You can just fit them, although what I just said about the random effects applies in the generalized linear mixed model case, right? You're going to hit some computational bottlenecks if you start fitting very complex random effect terms in a generalized linear mixed model, but you can do that with mgcv. Not really sure about that one. Are there any assumptions that need to be verified? Well, yes, and I talked about them a little bit at the beginning. So we make some assumption that the observations follow some distribution, or given the model have some distribution. So, if you choose Gaussian and your observations are not distributed Gaussian, then that's a violation of an assumption. Also, most of these models that we're fitting, that definition of wiggliness that I used, the squared second derivative, that assumes that everything is sort of just smoothly varying. We don't allow things to jump up and down. And so if the true effect is some piecewise linear function, or it's some stepwise function like this, then you're fitting the wrong kind of model there. Okay. Also, all of the modeling assumptions that you have with a generalized linear model, that's still there for the GAM, right? So the assumptions of the GLM are there for the GAM as well, and we have to check them. And so all of the regression model diagnostics that we would do, which we'll now do some now, those have to be satisfied as well for the inference to hold. Okay, someone's asking about the gamma argument. So there is a gamma argument in MGCV and GAM, and this basically just allows you to make your degrees of freedom, each basis function in your model, you allow it to, rather than just each basis function representing 1 degree of freedom, you allow it to use more. And so I think the typical value people use would be something like 1.4 often. And this comes from other areas of smoothing, and Simon's added this in. I haven't used it very much, but if you want to just put extra penalties in there, then you can change the gamma argument to be, say, 1.4, and then it will just, you're paying an extra penalty for complexity. You're not just using the 1 degree of freedom, you're actually paying a bit more of a price for each degree of freedom. Okay. It's blurring a little bit because when we're using the penalty to the actual smoothness parameter to shrink those coefficients. So each of our basis functions in the end doesn't actually use a full degree of freedom, but the gamma just puts more penalty in there. Some of these are getting a bit in the weeds, but I can answer some of those at the end. So it's probably better if I move on. So beta distributed, I've mentioned that you can use the beta R distribution if you've got these continuous proportions. So if you want to fit the beta regression model, then that's fine. You can do that using the beta family. Someone's asking, is a GAM without a smooth term exactly the same as a GLM? Yes, up to the algorithmic implementations, but they should be. Yeah, they'll be. If you don't put any smooth terms in, then the GAM should give you something very, very, very similar to the GLM. Yeah. It's using an iteratively reweighted least squares algorithm, which is exactly the same algorithm that GLM is using. So it should be the same, but they'll be implemented slightly differently because GAM's designed to do smooths. So there might be very small differences at times, but they should give you the same model. And mathematically, if you've got the GAM function without any smooths in it, if it's just got parametric terms, mathematically what we've written down there is the same as a GLM, and it's estimated in the same way. Is there a limit to the number of levels for random effects? So there isn't a limit in GAM. There isn't a limit to this random effect basis. You can have as many as you want, but the more you have, the slower the fit will be. And it doesn't degrade nicely. It doesn't go linearly. It actually starts to take longer and longer to fit as you add more and more levels in. But 3 or 4 levels of a factor as a random effect would that'd be fine. Yeah, it's if you've got more than tens or hundreds of levels of a random effect. Okay. Okay. So I think we'll move on now and look at some model checking stuff. Keep adding your questions. If you could ask your questions, put them at the end of the document now, so I can just go to the end as we go on. So if you've got questions that arise about these new slides, then put them at the bottom of the document, and I can find them more easily. Okay, right, so model checking. We have this GAM. How do you know you have the right degrees of freedom, i.e. you set up the K right? And then how do we diagnose model issues? So this is the same sorts of model diagnostics that you would be doing for a GLM or a linear model. We still need to do those for a GAM. So we're going to tackle these two things separately. So GAMs are just models, even though we've relaxed this assumption about how we specify the model. We don't have to specify the exact functional form. We let that come from the data. But they're still regression models. They still have assumptions, and we have to meet those or check that our model meets the assumptions. So this is actually from a slide that Eric Peterson created for one of our GAM workshops. But it's just showing, you've got data that have been simulated and then a model, the correct model. So this is where we've fitted the right model to the data. But here it might be we've fitted a particular model to the data, but we don't have the distribution right. So here the data have been simulated from a t distribution. So they've got more outliers. The data fall further away from the mean. Okay, and so this is where we fitted the wrong distribution because we've assumed it was Gaussian, but the data were actually simulated from t. So this one, we want to identify that. Here we have a setting where the variance isn't constant. So we have this thing called heteroscedasticity, where the variance is much larger here than it is at this part of the curve. Okay? Or we have dependent data. So we have time series or spatial data, and we don't model all of that spatial or temporal dependence. Or we might have the wrong functional form. So here we see we've got a data with a step change. There is a mean shift here in the covariate. And a GAM, therefore, because it's trying to be smooth, has just smoothed all the way across that step change, and that's the wrong model, right? In that instance, you wouldn't really have a GAM, or you'd have to have maybe a GAM in this bit and a GAM in that bit. So having like a bivariate smooth or something like that. But even that will be complicated where you don't have much data. You could include a mean shift in there as a parametric term, but you'd have to tell GAM where that mean shift should be. It can't estimate that shift from the data. There are packages that can do that, but not fit GAMs. So how do we test how well our model fits? Well, we're going to use some simulated data here. And I just want to explain this data. So we're randomly generating data. So we set a seed to make it reproducible, 400 observations. And then in x1 and x2, these are going to be our covariates. We're just creating Gaussian or normally distributed random values with mean 0 and variance 1, I think it is. Okay. And then we're going to have a function. So this is actually going to be some, the function here is actually going to be some sort of smooth function like this. It's just going to be undulating. It's got a cosine term in here. Okay. And then what we're going to do is we're going to add on some random noise. So we're going to create a data set that's normally distributed. So we're going to add on some normally distributed random noise. Then we're going to create a data set that has the same functional form, but it's going to be distributed negative binomially. So it's going to have, this is going to be count data where the mean follows this mean function. Okay. And then we're going to create binomial data, sort of 0, 1 data. So you have the same functional form, but we're fitting different, we're generating different kinds of data from the same underlying functions. And so this is what the data look like. Here we have, this is the Gaussian case. So we have this cosine term, so it goes up and down. And then we had this sort of slightly wiggly, potentially, there's a lot of spread though, a potentially wiggly term here. And then this is what these things look like if you turn them into negative binomially distributed data. So these are counts. So you get these high counts. Likewise, as you increase the value of x, you get these high counts. And then this is what it looks like if you have a binary data. All right. So we're going to use these as examples throughout the next few sets of slides. Okay. So the first part is, do we have the right functional form? And this, there are sorts of many things we might want to do. We have to, when you fit your GAM, you have the K. So we have the number of basis functions we use. We have the right, do we have the right distribution? Do we have the right type of smoother? Usually for most of these things, you have the right type of smoother. Most of them will do the same sort of job, although there are some types where you might actually need the adaptive smoother or some special type of smoother, so that's something to think about. We want to know whether we've got the right family and we've got the right degrees of freedom, okay? And then see if we're missing effects. Is there still unmodeled variation in the response that we haven't accounted for? So first thing we'll look at is setting the basis size k. So you typically would set k per term, and usually people often just leave them at the defaults and then hopefully go through the process I'm about to go through with you to check that the k was large enough. Ideally, when you start working with these in a lot more detail, you'll actually get better at choosing k up front. So here you might set k to be 10 or k to be 100 when you've got this sort of spatial thing. And you know, I said you should set k to be large enough to include the expected wiggliness, and the penalty will remove that extra wiggliness up to a point. It can't be, it's not perfect, but it will get rid of that, some of that excess wiggliness. But the bigger k is, the more slow the model fitting will be. So it's important that you check that your k was big enough. And mgcv has, in this gam.check function, it has a heuristic check for this. And so what it does is it basically takes the residuals from the model and then randomizes them and then looks to see if there's any sort of relationship with the covariate x or x1 or x2 or so on, yeah. And it does that, and if and assesses how significant. So if the associations or the relationships with x1 are larger in your residuals than they are in the randomized residuals, then it suggests you've got some unmodeled variation. Basically, it's looking at how observations nearby one another can predict the observations nearby that target observation, right? And so what is a heuristic? It's not perfect, but it is a good idea, a good indicator of where things might be going wrong in your model. Okay. So you get a lot of information about how well the model fits, and some of this, well, most of this, I'm not going to look at this at all. What I'm going to focus on is this stuff at the bottom. So when we fitted our model, we're going to fit it to the normally distributed data to start. Here I'm setting smooths of x1 and x2, and I've arbitrarily made them low just to illustrate this process, okay? So we've set them really low, and this is saying, you know, my expectation is that I don't expect much wiggliness. So when we do this, the reason we set k to be 4, but the reason k here, this is the maximum degrees of freedom that it could have taken, is 3. There is a term in the basis functions for each of these that is essentially the equivalent of the intercept, the constant, the flat term, right? There is a flat basis function in each of these. And so what GAM does internally is it just creates the basis with the 4 basis functions that you expect, and then gets rid of the ones that are confounded with the flat function, right? The constant, the intercept. So that's why you tend to have one fewer. Some of the other basis functions, like the cyclic ones, they'll be lower still, but that's the general idea. Okay, here. So this is the maximum wiggliness that you could have had. And then this is the estimated wiggliness in the model. And then this here is the k-index, and then this is a p-value. This is the randomization test, and the p-value is telling you, or rather, this is the measure for your data, and this is telling you whether that's significantly different from if you were just to randomize the data. And so here, what we're looking for, if everything was fine, then the k-index would be 1 or greater. And here it's really low. So this is telling us that we've got a problem here, right? This is telling us that we've modeled with 1 degree of freedom, so we've got a straight line in here, and this is telling us that there's lots of extra structure in the data. So this is telling us that the initial k was too small. We need to increase it. For this one, it says, okay, well, given what we've fitted, we don't need to do anything for x2, all right? So we should refit the model by increasing k for x1. So we go and do that. And you could double k, or you can make it quite large. And I'm just going to create it a bit larger so that we can move on quickly. We don't have to take too long doing this. Okay, so now when we do this, it set it to 12. So the maximum wiggliness could be 11. We use about 10.8. So now the fitted function is much more wiggly. Okay, the k-index is essentially 1, and the p-value now is large. So it's suggesting that this is just under the, if you were randomizing the residuals or the value, the residuals, then you would expect to see a k-index this large about 38% of the time. So that suggests there's no problem with this. What's happened now, though, is that it actually says, well, we now have a problem with this one. It thinks that the smooth for x2 is actually isn't wiggly enough, right? So now we need to change x2. So we do that, we increase x2. I just did the same thing. I just bumped it up to 12 to see what happened. Okay. Now we have 11 degrees of freedom as our maximum, 1 minus k. Yep. Now we use 8 degrees of freedom. This is essentially close to 1, and the p-value suggests there isn't anything going wrong here. Okay. So what was happening as we were going along? So each line here represents the fit from one of those models, and I fitted 3 of them. Okay. So the first row was that first model where I set k arbitrarily low. So this is what the function sort of looks like, really. Okay. But because k was so low, it couldn't possibly capture this amount of wiggliness, and so it just got penalized back to almost a straight function, straight through the middle here. So that's what went on. But all of that wiggliness structure was still in the data. All of the wiggliness that we simulated in the data was still there. And that's why that test showed that the k was really too small for x1. Now this one here, this is actually quite close to the observed function, but given the fact that this was so badly fitted, we couldn't really assess how well this was fitting the data, whether k was large enough here. So when we increase k, we do a much better job of picking up this cosine sort of function. But now it said that this wasn't flexible enough. Okay, and actually the reason that it isn't flexible enough is that this is the function. This is very close to the true function, right? And you need extra degrees of freedom to make the line go flat. Here you had fewer degrees of freedom, so the curvature can't change. So this curve here has got sort of a very smooth curvature at that point. Whereas here, because we're changing the curviness, this is actually a more complex smoother. And to represent that, you need more degrees of freedom. And so that's what it picked up. Once we'd got this term correct, or close to correct, then it picked up on the fact that we didn't have this one complex enough, and then we fixed that. Okay? So this iterative checking is something that you need to do with your model to make to check K. Now don't sometimes you get led astray, especially if you're doing time series or spatial models. It might keep indicating that K needs to be bigger and bigger and bigger. Don't get deluded by that. Sometimes that's just telling you you're just modeling the autocorrelation in the data, and you might actually not want to do that. And so you might want to do that in another way. So you don't have to keep setting K larger and larger. And another thing that you can do is if you don't want to trust the heuristic, this test that Simon has created, then one thing you can do is you can take the residuals from the model, okay, and then refit your model, but now the response is the residuals, right? And now those residuals, because they're deviance residuals, they should be approximately Gaussian for most families, not for all. They'll be roughly. So you change the family to be Gaussian, and then if you refit your GAM with the smoothers, right, then if they detect any nonlinearity, so if any of the functions use more than 1 degree of freedom, it suggests that you've got extra wiggliness, and so those are the functions that you need to go back and increase K for. So that's an alternative way of doing this check. Okay, so model diagnostics now. So this is the visual checks that come out of gam.check. What are we looking for? So in gam.check, it gave us that printed output that I included in the slides, but it also will create 4 plots. And it creates a quantile QQ plot, quantile plot of the residuals. If the model is essentially right, it should follow roughly the 1-to-1 line. It produces a histogram of the residuals. For many of these distributions, these deviance residuals should be approximately Gaussian. For things like binary data and stuff like that, they won't always be distributed the right way. So the histogram can be a little bit misleading, but yeah, for a lot of these, they should be roughly Gaussian. But for count data with low counts or binary data, then the things can deviate quite a lot from that Gaussian assumption. Right? It then also plots the residuals versus the linear predictor, and it also gives you a plot of the observed versus the fitted values. And all of these are useful for sort of diagnosing things. Now, they're not exhaustive. There are other plots than things that you could do, but gam.check gives you these ones. Okay. And so if you do that, this is what we get. So I'm showing here an example where we are fitting a Gaussian model to those Gaussian data. So this is Y norm. This is the thing we've just been looking at. So I've got K set large enough, right? And when we do gam.check on our model, then we get these plots here. And if you set the rep equals 500, so here I'm doing, I'm actually simulating data from the response and creating confidence intervals on the QQ plot. That's what the rep is doing here. And so this now gives you a confidence band. There will always be, in this QQ plot, there'll always be some random variation from the theoretical one. And you want to just see, well, okay, if I generate data that is, in this case, Gaussian, if I generate Gaussian data from my model, what does the QQ plot look like? And so these are confidence intervals on the QQ plot, right? And so they fit in within the confidence interval, suggesting there's no problems. This here, we're looking for things like an increasing, getting wider, spread getting wider as you move along the linear predictor. This looks all fine. The histogram looks roughly Gaussian, so that's okay. So just 1 second. I'm at home with my kids, so alone. So I just need to answer a question. Sorry, 1 second. Okay, so sorry about that. Guess everyone who's got kids is experiencing these kind of things. Where was I? Okay, yeah, histogram and residuals. This looks roughly Gaussian, and here we see, sort of a roughly 1-to-1 fit. We're doing pretty well, but there is obviously some random noise in here, but we do a pretty good job. Okay, so these would be good diagnostic fits. They would suggest that there isn't a problem with the data, and in this case, because we fitted a Gaussian model to Gaussian data, we should expect that. right? Here's an example where we fitted the wrong model. So we have the negative binomial data, it's counts. So and one thing we might start off doing here is to fit like a Poisson model. And here we see where the diagnostics indicate that there are problems. So clearly we've got the wrong distribution. These tails are much heavier than the theoretical distribution. And so if we'd actually, here we're simulating Poisson data from the model, because we fitted a Poisson model, that gives us this band. And here we see there's a lot more over dispersion. There's much more variation in these data. So it tells us that the Poisson model here is not the right model. And we can see that in some of the other ones here. The residuals, much heavier tails, and there is a non-constant variance effect going on in here. Okay, so we clearly don't have the right model. Now if we change and we fit the negative binomial model to the data, so we use family equals NB and rerun the gam.check, now things look much better. All right, we have some slight variation, so it does go slightly outside the confidence interval here, but that looks pretty good. These tails are not as heavy, so the tails are not as heavy out here, suggesting that our residuals are a bit more Gaussian. Now they're not going to be perfect because we still have these low counts. These are in the integers, so these values, these low counts, that's like zeros and ones and stuff, they're still going to be present in these deviance residuals. You can't do anything about that, but there doesn't look to be the same kind of fanning out, this widening of the residuals as you move along. Here we see the residuals getting wider and wider. That's a bad plot. Here they don't really seem to do that. All right, we'll still see this pattern because of the integers. The only way you can get rid of that would be to use sort of randomized quantile residuals or something like that. Okay, but those are not available in mgcv directly. And here now this is our fitted values. Now we should expect there to be heteroscedasticity. We should expect more variation at higher counts and a lot of it. So but the idea is that they should lie on a one-to-one line with the line going through sort of the middle here. Okay, so those look good where we have. So these are the things that you're looking for in your model checks. So it's making sure that, and if there is some pattern, if there was some non-linearity in here, yeah, then that would suggest that you're missing, you haven't got K maybe large enough, or you're missing some covariates if there's some structure in here. So those are things that you're looking for. But all of these plots for this model look great. These are bad. Okay. And I just want to point out, I've got a package called Gratia, which uses, well, there's an appraise function in there, which does the same job as gam.check, or the plotting part of gam.check, and it just does it using ggplot. And so you get ggplot versions of those things, but it's doing exactly the same kind of methods under the hood. Okay. So let's just have a look at our Google Doc and see if there are any more questions. Just 1 second. Okay. Sorry, I'm home alone with the kids and I just got a message on my phone about something, but we'll deal with that later. Okay. So someone's asking, in gam.check, is rep equals 500 a reasonable starting point for the visualizations? So that rep equals 500 is only going to affect the QQ plot. And that's fine. If you've got a big data, you might even want a biggish data set, you might even want to set this to be relatively smaller than that. But 500 is okay. Yeah, but and that's fine for a credible interval. I mean, if you really want to have a very accurate confidence interval on that QQ plot, then you'd need really to set the reps to be in the tens of thousands. Okay, so but it really just use it as a guide. 500 or 1000 is fine. Even 100 might be fine. Just accept that if you have low 100 or 500, then you might see some areas where even if you fitted the right model, you'll get some slight deviations outside of that credible interval or confidence interval, sorry. Okay. And if you're worried about that, then you could obviously redo the gam.check and increase rep to see if it's still there. But you know, don't worry too much about it. It's more in the case of the Poisson one here, where it was grossly outside the confidence intervals. In that instance, that's indicating that would be a bad plot. That would be a bad diagnostic. Small deviations, like you can't really see them so well on the slide, but there is a sort of slight deviations here that might get picked up and dealt with if you had 1,000 or 2,000 reps. But it's overkill, really. You're not, those are only small deviations and you don't need to worry about it. Someone's asking about the bi-factor variables. So what I described, oh, I won't go back, it's a long way. But what I described for the bi-factor is if you just had an ordinary factor, okay, I will have to answer what I said there about bi-factors was if you have just an ordinary factor. If you have an ordered factor, then you need to set the model up in a slightly different way. I'll answer that in the Google Doc, okay? So if they're binomial GAMs, someone's asking about suggestions for diagnosing them. I mean, if you've got a binomial GAM, like it is literally 0 1s, like a Bernoulli, then there isn't much you can do unless you can aggregate, like I did in the LARCS data. I think the sort of randomized quantile residuals that you can get with the Dharma package can help with that to some extent, but I haven't looked at Dharma in enough detail to say about that one. Okay. So let's crack on. We've got a little bit to go, and I want to try and leave some time to go through some examples. So I might skip over some of the model selection stuff now as we go along. But okay. So when we're fitting our model, we've done all these things. We've checked K. We fitted our model. We checked K. We checked the family. Done all of that. But we still might want to decide whether we need to include terms, or do terms in our model have a significant effect or not, or I mean, we want to get away from having this dichotomy of things being significant or not. So, but still, we just want to know whether the effect might be 0 or not, right? And often when we're doing this frequentist sort of statistics anyway, we're trying to aim for a balance between fit and parsimony, i.e. we want our model to fit the data well, but we also want our model to be relatively simple. As one way you could approach this. Don't think that's necessarily the best way to do it. In applied research, we want to seek some sort of set of covariates that have the strongest effects on Y. I mean, we might have some hypotheses to test, and we might want to see whether we fit a model that embodies those hypotheses, and then we see what the effects are. Okay, so we might want to do some model selection, decide whether a term that we've put in the model, is it having a reasonable effect on the response or not. So we're going to talk now about shrinkage and additional penalties, because one thing you really shouldn't do with these models is, with any kind of regression model really, is to, unless you're just interested purely in prediction, is to fit the model and then use some forward selection or whatever and drop terms in and out of the model on the basis of that forward selection. Okay, might work for prediction, but it's not going to work well if you want to do inference. So what I want to talk about now is a way that we could do the selection in the mgcv software through the use of this penalty. We already have penalties that are shrinking the coefficients, making things closer and closer to bilinear. Can we modify those penalties so that we can make them closer and closer, not just to linear terms, but to flat terms of no effect, right? So with this smoothness parameter estimation, or the penalized regression that we fit, we can fit a wide range of potentially complex functions all the way back down to a smooth function. But we can't remove a term entirely from the model because of the way the penalties are constructed. So the penalty I said was on the wiggliness, and so the wiggliness was measured in terms of that curvature, right? The second derivative. So if you have a flat function, right? If you have a flat function, sort of some linear function, so by flat I mean some straight line or something like this, those functions don't have or the second derivative is 0, so there is no penalty there. So the penalty itself, it can't affect those bits. So that in technical terms, the penalty only works on what we call the range space of the spline basis. So it's only working on the bits where the penalty is not 0. The null space is unpenalized. So the null space represents functions that are perfectly smooth, like the constant or the linear term. The range space represents the basis functions that are wiggly, okay? And we can only penalize the wiggly bits. So there are ways that we can also penalize the null space. And one of them, the best one really, I think, but you have to turn it on for every term in the model, is to use the double penalty approach, which we turn on by adding select equals true as an argument to the GAM function. There is another approach which uses special splines that have an extra penalty on, called the shrinkage approach. And these are shrinkage splines, and there are only two of them, I think, in mgcv. One of them is shrinkage version of the thin plate splines, so you'd use TS as the basis. And we have a shrinkage version of the cubic spline as well, so we'd use CS. And Simon Word and Jean-Pierre O'Mara have done work on this. They found that their double penalty method tended to work best, but you have to apply it to all the smooths in the model. And it doubles the number of smoothness parameters you have to estimate. So if you only want to do this shrinkage or selection on some terms, then maybe you just turn it on with these special bases here. And there are other shrinkage selection approaches than the ones I'm talking about here, but they may be available in other software and not in mgcv. So where does this come from? Well, that matrix, that Sj, this penalty matrix that I talked about earlier, when we're thinking of it from a Bayesian point of view, we can think about that penalty matrix as being a prior as a prior precision matrix on the basis functions. So it's like a multivariate normal prior, right? And then our lambda j's, our smoothness parameters, which we have for our different smooths, that's actually an improper Gaussian prior on the spline coefficients. So it's an improper prior because the penalty matrix isn't actually a full rank. We get zero eigenvalues. And the reason it's not full rank is because it includes this null space that isn't penalized, right? So this really is an empirical Bayes with an improper prior when we fit it using mgcv. You can be fully Bayes when you do it in the fully Bayesian software, but in mgcv it's this empirical Bayes approach. Now what's going on when we use the double penalty or the shrinkage smooth is that we try to remove that impropriety from that Gaussian prior. So we try to penalize the null space as well as the range space so that the penalty matrix is then of full rank, okay? And that's what's sort of happening. And then in the motivation, and so with the double penalty, what it's doing is it's just adding an extra penalty onto the null space, that it only affects the null space. So we have a penalty that affects the wiggliness bits, and then we have a penalty that affects the smooth bits. And that's added to each smooth, okay? Now in the double penalty, that makes no assumption about how much you shrink the null space relative to the wiggliness, the range space. And that's entirely determined, how much you shrink both bits is entirely determined by the estimation of these extra smoothness parameters on the null space. Whereas if you're going to use that shrinkage smooth approach, it assumes that the null space, the linear bit, should be shrunk less than the wiggly part. So it's going to shrink the wiggly bits more than the linear bits. That's the main sort of practical difference between these two things, other than that you having to add the double penalty to every smooth. So Jean-Pierre O'Mara and Simon Wood have shown that the double penalty and the shrinkage one approach works well. They work better than a lot of the alternatives, and they also work well in terms of this variable selection. So actually they could identify terms that needed to be removed from the model. I had no effect on the response. So what I'm going to do is show you a quick example of that before we move into some of the other examples. So I want to simulate some Poisson counts. I've got 4 known functions, and they're not shown on this page. I'll show them on the next slide. We have 4 known functions, and then 2 spurious ones where I've just generated uniform data. And they are actually shown on here. So that's what this code is doing, and I'm going to fit the model, all right? So I'm fitting the model to these, okay? And here's our plot of these functions. So this is our known functions 1, 2, 3, and 4. So this is a known flat function. And also these ones are also known to be flat, but I've just added them in as extra random. So there's no relationship between any of these 3 functions and the response, but there is a relationship between these 3 functions and the response. Can we recover these 3 functions while still not estimating any effects for these 3? Well, if you look at the summary for that model that I just fitted, and I did this by turning on, one thing I forgot to say is I turned on the double penalty using select equals true. So this adds a penalty to the null space of each of these 6 smooths. All right. So if we do that and we look at the summary, well, we still see we estimate here these are nonlinear effects for the first 3 terms, so they should be nonlinear. And then we effectively get 0 terms. These degrees of freedom, the effective degrees of freedom, have been shrunk back well below 0 for each of these three terms that we said had no effect. So if we just look at the model outputs, it seems to have done a good job. It's identified the ones that do have an effect on the response, and it said, well, these other ones here don't really have an effect. And they've been estimated to have no effect because their degrees of freedom are essentially 0, right? But notice that the reference degree of freedom column is all set to 9. Each one of these had k equals 10 at the default, so I'm paying the full price. 9 degrees of freedom is the price I'm paying to have each of these smooths in the model, even though these ones here use almost no degrees of freedom. What this is doing is it's taking into account the fact that I didn't know. I thought they could have used 9 degrees of freedom each. I didn't know how many, and so it's using that in the test. So it's actually accounting for the fact that we've done the selection in the model, in the p-values here. What functions do we get estimated? Well, here I'm loading Gratia just to draw these a bit nicer so we get the titles on. If you draw this using the draw function, draw our model, then this is what you get. And actually this has estimated these functions pretty well. They're pretty close to the actual functions. And then these ones have all been estimated to have essentially 0 effect, right? So that's how that selection works. Now, of course, this was perfect data, or almost perfect data. It was simulated data where I knew what the effects were, and I had a lot of data. And these effects are relatively strong, except for these three, where there are no effect. But it did work. And in the simulations that Giampiero and Simon did, it also worked really well there. It's not going to work perfectly in every data set, but this is a way of doing selection on your model whilst accounting for the fact that you've done the selection. Okay, just have a quick look. So someone's saying after using select equal true, the p-value decreases. And how should using this double penalty shape our interpretation of the p-values? Well, the p-values should be fine. I mean, they're essentially taking into account the fact that you've done the selection. The reason they're smaller, even if the functional shape hasn't changed. So if I'd fitted a model that only included, these first three smooths in it, in the data, then, and I hadn't done select equals true, then my p-value, I'd only be paying the number of degrees, I'd only be paying roughly this number of degrees of freedom, right, as the penalty. So this number of degrees of freedom is my complexity. So my p-values would be perhaps higher. In fact, actually, these would be a little bit higher in that model, right? So the p-values then wouldn't be, they would actually be lower than when you use select equals true on all of this thing. Because now, when you use select equals true, you're paying the full price. You're actually saying that I use 9 degrees of freedom, okay? That will make the p-value change. It can also improve the p-value. You might get better, so the p-value might get lower, and therefore, i.e. they become more significant, if you want to use that term. And that can happen just where there are nuisance terms, and sometimes that you might estimate it as a linear term. Okay, it might get estimated as linear because you can't estimate, you can't shrink back to this flat function, but that linear term might be correlated, or that linear effect might be correlated with some other terms in your model. And so really, because you're estimating this effect incorrectly, then you can't estimate the other smooths correctly. So by adding the select equals true, putting that extra penalty in, it might allow you to correctly identify those terms that have no effect, and allowing the other terms to model that variation, that their effects fully. It's not getting that effect is not being mopped up randomly by these other terms. So that the p-value can change. I mean, you just treat the p-values in the same way as I'm going to talk about now. Treat them in the same way, essentially. But just note that you're paying the full cost of the original basis for doing it. Therefore, you're taking into account the selection to some extent. Okay. So these confidence intervals that GAM produces, they are approximate 95% intervals given this plus or minus 2 standard errors. But what do these intervals look like? Well, Doug Nitschke and Grace Waber and Brian Silverman have done a lot of work on this. And Doug Nitschke showed that the intervals that Grace Waber and Brian Silverman discussed in their Bayesian approach to smoothing have what are known as good across the function frequentist coverage properties. So what do I mean about what is across the function? So typically a frequentist confidence interval has point-wise coverage. If you look at one point, it will have, say, 95% coverage on average. If you were to repeat the process and create hundreds of those intervals, 95% of them would, if that's your alpha, would include the true function, 95% of those intervals. What Dugnichka showed was that for the Gaussian case, that this across the function property, it means rather than looking at just point-wise, just one position, it means that if you average the coverage over the whole smooth, it has approximately 1 minus alpha coverage. So if alpha is 0.05, you want a 95% interval, then on average, the coverage is 95% over that interval, okay? So that's what the across the function is. So it basically means these are Bayesian credible intervals, but they have this interesting frequentist property that the average coverage over the whole curve is roughly 1 minus alpha. And in some other work by Jean-Pierre Amaro and Simon Wood, they extended Dugnichka's work to the generalized case and also explained where the coverage doesn't work very well. And so it works really well in many situations, but there are a couple of situations where the confidence intervals don't really work properly. One is where the penalty, the penalty is approaching essentially zero. So it's not quite, approaching infinity. So it's almost back to a linear function, but not quite. So it's where the true function is almost in the null space, close to a linear function. There the coverage can get bad in places. And also there is this problem where if you have highly correlated covariates, the coverage might be wrong as well. In the interest of time, I'm going to skip over this. Basically, this across the function thing works. Just don't over smooth, but also the effect of the uncertainty, because we're just estimating the smoothness parameters, we don't know what they are. Yeah, there's some extra uncertainty. That extra uncertainty is actually rather small and wouldn't, if we accounted for it, wouldn't actually change the credible intervals that much, basically. Where the effect of that uncertainty is small, the credible intervals would have the right properties. Okay. So some of you, and this has been mentioned in the comments, some of you asked what happens when the credible intervals, the confidence intervals on the smooths, they go to a point, they look like bow ties and they narrow to a point where they're essentially saying that there's zero uncertainty. Well, that's a case where that linear term is inside the null space. And in that situation, that's where the default credible or confidence intervals fail. They can't possibly have zero uncertainty at that point. They have to have zero uncertainty just because that's where they're centered in that credible interval. But that's just a problem with the way we create those intervals. So there are some things that you can do. If you do SE with mean equals true in your plot.gam call, or if you're using Gratia, you say overall underscore uncertainty is true. What we can do is we can actually include the uncertainty in the intercept as well as the uncertainty in the smooth when we draw the plot for the smoother, and that then gives better credible intervals. And so here, I apologize, this has actually got a little bit small because they're all on the same scale, but here this curve is close to the the true function is close to being linear. This one is linear, okay? And you can see that the credible confidence intervals come close to they actually cross and become negative. They become zero in width at zero, where the smooth crosses zero. Likewise, these ones, they have this bow tie thing. And then the bottom line here, I'm turning on SE with mean equals true. I'm turning that option on. And now you see these intervals now don't ever, they shrink, but they don't ever come to zero. And so that's an option. And I think this overall uncertainty equals true. I think that's the default in draw, because it doesn't really change things when they're really wiggly like this. It doesn't make them any different, but it does have an effect on when they're linear. And so I think I've added that as a default, but it's not the default in plot.gam, which is where these things were created. Okay. So let's look at p-values from smooths and comparing models. I just want to briefly explain what the output from summary is. These p-values, so this was the model where we had those 3 redundant terms. what these p-values are, in all cases, they're a test of the null hypothesis that there's a flat function, that the true effect, we're saying the true effect is some flat function where there's no effect of the covariate at all, and then how likely is it that you would have got a result this big, i.e. you would have seen a smooth like this if the true thing was this. Okay, so in the instance here, the first three of these, it's highly unlikely that you would have seen that. Whereas for these other three functions, they've been estimated as flat functions. They are highly likely to have been observed if the true function was flat. Therefore, the p-values are really quite high. Okay, so these are special tests that have been designed. They have good properties for these GAMs. A couple of things to note. They don't account for the estimation of the smoothness parameters. So when we calculate this p-values, we treat the p-values, the smoothness parameters as being known. And so hence the p-values are actually biased low. They're a little bit smaller than they should be. Okay, so that's one thing to be careful of. So if it says 0.05, then that's a bit low. The real p-value should be a bit higher. And they also rely on asymptotic behavior. So basically what this means is they tend towards being right, i.e. the p-value is correct, as the sample size tends towards infinity. No one has an infinite number of data, so just treat them as being approximate. In the same way that they're approximate in a GLM, they're approximate in a GAM, but in the GAM we have this extra issues that we had to estimate the smoothness parameters, and yet we calculate the p-value given the estimates of the lambdas. We treat them as being known. So they're approximate. Don't fret too much about whether it's just below 0.05 or not. Don't worry about it like that. You really want these things to be well below 0.05 to identify effects. Said that, yeah, I'm going to, and these things, the p-values in the summary, they rely on this theory for the confidence intervals I was just talking about. So if you haven't undersmoothed and the things are not essentially linear, then they work really well. That they fail, that the p-value doesn't quite work as well, where the credible intervals fail or don't quite work as well. Okay, so you have to just accept that. And the test statistic is actually a chi-square statistic, but it has a very complicated set of degrees of freedom. And so just quote the output from the summary. Okay. Where these p-values would break down is if you have entirely unpenalized terms. So this is for things where you have Gaussian random effects in the model. And what Simon Wood has proposed is actually a different test for these unpenalized terms. And this is basically based on something like a likelihood ratio test. The reference distribution that Simon uses when he's doing these tests, so the null distribution in a sense, it is actually corrected for this null hypothesis of testing on the boundary of the allowed parameter space. Basically what this means is that because these are random effects, the variance can't be less than 0, right? But the tests in LME and LME4 assume that 0 is in the middle of the range. Well, Simon has corrected that here, and so you don't have this testing on the boundary problem. So it corrects for the fact that the null hypothesis is a variance term of 0, which is on the edge of the allowed parameter space, right? So it's corrected for that. So the p-values are slightly different to what I just described for random effects, but they have been corrected for this testing on the boundary problem. Okay, and where do the p-values work best? They work best when we've got ML smoothing, and then they are slightly worse when we use REML smoothing, and then they get worse if you use other things. Okay, and so ML and REML should be the ones we use, and really REML is the sort of default we recommend. Okay, a couple more slides before I move into a couple of examples at the end. So AIC, we can use AIC, and Simon's actually done quite a lot of work, and his colleagues have done quite a lot of work on AIC. Usually the AIC that you would have had a few years ago from mgcv and in the GAM package as well, it would have used the likelihood of the coefficients conditional upon the smoothness parameters, i.e. Ignoring the fact that we estimated the smoothness parameters. Okay? And this conditional AIC tends to choose more complex models, and it especially will choose complex models where there are random effects in there, right? And so really that's not a good idea. You don't want an AIC criterion where you're always going to select the most complex model. So what has happened in this more recent paper by Simon Wood and colleagues is that they've worked out a way to correct the AIC for the fact that we didn't know the smoothness parameters. They were estimated from the data. Works reasonably well. In fact, it fails only in the situation, or it works less well in the situations where the credible intervals don't work so well, or the p-values aren't quite so correct. But you can use AIC to compare GAMs. So in this example, remember these last three terms had no effect, right? So I've got B1, which is the full model. B2 is where I've removed these terms that had no effect, okay? And then I have estimated I've got the AIC. So we see we actually saved ourselves about 3 degrees of freedom, and the AIC actually chooses this simpler model, okay? It says that we don't need those 3 terms, okay? And when there is no difference between the models, then this AIC will accept the larger model, so the more complex model, about 16% of the time. And this is consistent with the probability that AIC chooses a model with one extra spurious parameter. So the probability that you have this extra parameter, it will choose it. It will do it about 15.7 or 16% of the time. So in their tests, they showed that it does exactly what AIC does with any other kind of model, like a linear model or whatever. 16% of the time, it'll choose the more complex model, even when there's no real difference between them, right? For this spurious parameter, sorry, one extra spurious parameter. So just be aware of that. AIC is based on prediction, and it doesn't have this 95, it's not like a 0.05, like 5% of the time. It actually will choose the more complex, i.e. get it wrong 16% of the time, okay? But we can interpret this AIC in the same way as we would with a linear model. Okay, I've got 2 examples that I want to go through now, and I'll go through this first one relatively quickly because it's relatively simple. It's a data set of atmospheric CO2 data. So we've got the CO2 measurements at Mauna Loa. We have a time variable here. This is just the cumulative months. It's just adding up. So for every month of observation through over many, many years, it just keeps adding up. So this is going to be our time variable. And then there's a variable here which tells you what month of the year we're in. So this goes 1, 2, 3, all the way up to 12, and then starts back at 1 again for the next year. Okay. And this is the data. I've just plotted the data in ggplot. So there was some missing data at the beginning. Okay. And then this is, what we've seen in terms of atmospheric CO2 increasing. And then there is a seasonal pattern in here, which is related to the growth of the large boreal forests in the northern hemisphere. They suck up a lot of CO2. So if we just fitted our naive GAM, we might want to say, well, I can fit a really wiggly function that's going to get all this seasonal term, and it's going to get the long-term trend. And I can do that in a single smooth because I can just use this cumulative month thing, right? So let's do that. Okay, so we fit that model. We need a lot of degrees of freedom because this is going to wiggle up and down and up and down and up and down all the time, right? So that's going to need a lot of degrees of freedom. So we set it high. And because there's relatively a lot of data and this is a large basis, I'm going to use the cubic regression basis. So I don't have to pay the price of having the thin plate spline basis to be created. Rest of this is as we've seen before. And when we fit this, great. We've modeled it. Looks really good. We explain almost essentially 100% of the variation in the data here, according to this thing, okay? This is great. Maybe we want to use our model to predict. Yeah, it'd be really good. Let's see, well, what does our, given the behavior so far, what does the model think is going to happen for the next 3 years? So we're creating some data that we want to predict at. So this is, and I'm going to predict that from month 1 all the way up to the end of the data plus 36 values on the end, okay? So that's for the extra 3 years worth of data. So that's creating a new data set with some, this is our predictor variable. We pass that in to the predict function. We're going to get some standard errors out as well. And then I'm just adding all of that I'm creating the upper confidence interval and the lower confidence interval for the fitted values and the predicted values all go into this object PD. And when we do that, this is what we get. So we get really good fit to the data here, okay? But then, we have a bit of a problem here, and that's because the end of the data, it just linearly extrapolated out, all right? This is one of the potential problems of using the GAMs, is that they don't extrapolate well. There are ways that you can actually try to control that, but they will just linearly extrapolate. So we have this really complex model that fits our data perfectly, but is useless for prediction. Can we do any better? Well, yes, we can do any better. We can do better. And one of them is to just think about this. Why should we treat this data as being a really wiggly thing? There's a lot of seasonal variation in here. Maybe we model the seasonal variation separate from the long-term trend. Okay, and that's what we can do now. So here I'm going to do a better version of the model, which uses a cyclic smoother for the month, what month of the year it is. So we're just saying that December and January are going to be the same, or similar, sorry. And then we have the same quite complex term, and I could actually have set this a lot lower because now we'd expect this to be a much more gradual trend for the long-term trend, okay? The only thing I'm doing extra here is that I'm setting the knots. So I'm setting the endpoints for my cyclic smoother, right? I'm setting them to be at 0.5 and 12.5. Basically, I'm just saying that 1 is the midpoint of January, 12 is the midpoint of December, and they should match just slightly outside that. They should just match at the beginning of January and the end of December, right? That's all I'm doing. And actually doing this actually works better. If you set them to be 1 and 12, then January can't be different from December, and January is different from December, right? So we need to do this little trick with the knots. When we do that, both of our smooths are very significant. So they've been, this is using 7 degrees of freedom, this is using 104 degrees of freedom. We still explain almost all of the variation in the data set, right? We go through our prediction step again. Now when we predict, we get something that's much more realistic, okay? Now, and that's because it's extrapolating using the sort of roughly simple trend that's been going on in the data, and the seasonal variation is there. Now, the reason that this term is still using 104 degrees of freedom, this is telling us actually that the seasonal cycle is changing over time. So there is some sort of regular seasonal pattern, it's going up and down like this, but the exact shape of that and the magnitude of the oscillation is changing over time. And that's why there's still a chunk of variation in here, okay? But now the model doesn't simply just extrapolate out linearly at the end. We actually get this seasonal term working on there. And there are ways that we could do that. We could have allowed an interaction between the year and the month, and then that would also have allowed, so we would have had a simple year term, we would have had a simple seasonal term, and then we would have a tensor product of month with the year, and that would have allowed the seasonal pattern to vary through time, and we could have done that model as well. Okay. This is the more complex example that I wanted to talk about before we finish, and it just illustrates, I think, the power of the GAM to handle quite complex data. Okay, and this actually came up as a question on the cross-validated website, which is like a Stack Overflow, but for stats. And so the opening bit is, I have a data set of water temperature measurements taken from a large water body at irregular intervals over a period of decades. And this is actually Galveston Bay in Texas. And well, the link, I'll fix this, but the link is actually hidden here underneath the image, but I'll fix that later. And so what I'm going to walk through now is the analysis I did trying to show them how they could actually model this complex spatial temporal data set. So we're just reading in the data. So I'm using the readr package, reading in the data. The data are available. They're in the GitHub repo. So if you downloaded it, you could just run this code. We're then doing a bit of converting. We actually have to create a date time variable because the dates and the times were as separate variables in the raw data. Across this bay, there are multiple stations where the temperature of the water was getting measured. So we want to create a factor from the station ID because we're going to use that in our model as a random effect, perhaps. or we could do. I'm creating a day of year. So this is now going to be used for my seasonal term. So I'm just formatting my date time and just asking for the day of year. This is %j. I'm getting the time of day out as well. So because these data have been taken, some of them have been taken in the morning, some in the middle of the day, some later on in the day, there's going to be some variation due to just when they actually did the sampling. And so I want to know what the time of day is. And so this is just a way that I get the time of the day expressed as a decimal. Okay. So now we've got our data created, we can fit our model. And this is the model I sort of suggested as an answer. So it's quite complex, and I'm going to go through the individual terms. So alpha is our model intercept. Then we're going to have some smooth functions showing how the temperature varies throughout the day. So depending on what hour of the day you were to take the sample, how does the temperature vary just with the time of day effect? Then is there a seasonal effect? So this is a smooth function of the day of year. So this is how the temperature varies through the year. Then we have a smooth function of the year. So this is how does it vary over the years in here. And then we have a spatial smoother. So this is going to account for the variation across the bay. Then we have an interaction between day of year and year. So this is saying how does the seasonal pattern vary throughout the over time. So sorry, add that here. How does the seasonal cycle vary through time? That changes. It's not going to be a constant seasonal cycle through time. It's going to vary. The spatial pattern can also vary with the different times of day. Some bits, if they're closer to the coast, for example, they'll warm up faster than ones that are further away from the coastline. So there may be a variation in the spatial pattern with the time of day. There may be a variation in the spatial pattern seasonally, yeah, and there may be a variation in that seasonal pattern, in the spatial pattern over time, a long-term change in the seasonal pattern. So this is a relatively complex model with lots of terms in it. It's actually relatively easy to fit using mgcv. Okay, so the first 4 terms effectively estimate the time of day, the seasonal effect, the long-term trend, and some spatial variation. And then the next 4 terms, they essentially measure how the seasonal pattern varies with the long-term trend, the spatial pattern varying with the time of day, how the spatial pattern varies seasonally, and how the spatial pattern varies over the long-term trend. And so when we fit this, we need to do the same trick with the knots, because I don't want January 1st to be exactly the same as December 31st. And I'm also making it account slightly for the leap years, so it doesn't really matter about that. This doesn't actually fully account for the leap years, but it's at least better than ignoring it. Okay. Then we're going to use the BAM function. BAM is for a big additive model. So if you've got lots of data like we have here, then the BAM function can actually fit models much more quickly than the GAM function can. So as our response is the temperature, and then we're just going to basically make a smooth function for each of the smooths that I showed in the formula in here. Okay, so we're going to have 8 smooth functions. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we've got a smooth now that maps onto our model. So we have this time of day, day of year. Now, the day of year is a cyclic spline. I didn't make the time of day a cyclic spline because you don't have observations at midnight and early in the morning. Okay, so we just left that one as being non-cyclic. We have a relatively complex trend, long-term trend, because there's a lot of variation over time in here. Relatively complex spatial one. Here I'm using a Duchon spline. And with these 2 properties here, it just means that it's not affected much by the boundary. So it'll work better at the boundaries of the space. Okay. And then we set up these interactions. Now, because things like day of year are already in the model here, and then I want day of year to be in this interaction with year, and I want day of year to be in this interaction with space, and I want year to be in the interaction with space, but I've already got a year term in the model potentially. Yeah, I want them to be in here. So year is going to appear lots of times. So in these interactions, I want to use the tensor interaction term because but I just have to make sure I have the main effects in. As long as I've got the main effects in, then I can add these more complex interactions, higher order interactions, and I'm not going to run into the same kinds of problems, the computational problems that we might have if we had, because if I'd used TE, we'd have the main effective day of year in here, and it would be in here, and it would be in here, right? So we want to do this decomposition because these terms turn up everywhere, because I want lots of different interactions. Okay, we want to use the fast version of REML with BAM, so that's the default, but we just specify it in here just to be explicit. Don't use method equals REML because it'll slow down a lot. I'm turning on an extra feature here which just speeds things up, and I don't have time to explain what that is. But then, and also I'm using some extra threads, and I'm not going to explain what that's doing either. It just makes it faster to fit. Okay, and then I can fit a simpler model here. We want to compare it, but here I've just got rid of all of these higher spatial terms, i.e. does the spatial pattern really vary over time? Okay, both within day, within the year, and between years. All we're allowing for is for an interaction between the seasonal term and the year term. Okay, so that's a simpler model. We fit them. They take a minute or two on. I've got a pretty pokey little computer at home, and I ran these and they still took less than a minute. If we compare using AIC, we compare these two models, then we see we actually favor the full model quite strongly. It's got a much lower AIC, almost like about 600 units lower. So that shows strong favoring the more complex model. And if we use the ANOVA function to sort of do a generalized likelihood ratio test between the two models, we also see that by removing those higher order interactions, we make the model significantly worse. It explains significantly less deviance. So there does seem to be some variation in the spatial pattern at all of those temporal scales. Okay, if we look at our model summary now, we see that these are all highly significant. So the terms are being estimated to be not, they're a long way away from being flat functions. That's great. And we do a good job of explaining the variation in this data set. Okay. Apologies, this is quite small on screen just because of the model definitions are big, so I had to shrink the font size down to get it on screen. If we plot our model using the plot.gam function, so we plot M, I want all of the terms on one page. I'm using this particular color scheme here, and then I'm shading the confidence intervals, so they're shaded rather than dashed lines. Then this is what we get, and it's a bit squashed up on here. You could move this around on your screen, but here we get all of the terms. There's only, what we got? We've got all 8 terms here. This is a new development in the plot.gam function. It can actually plot higher order interactions up to 3-way, and we have them here. Okay, so this is the time of day one. It's a bit hard to see exactly what's going on here, but there is an effect. This is the seasonal effect. Okay, and this is the long-term trend. So we can clearly see that the seasonal effect is the largest effect. Then there is lots of variation perhaps over time, and then there is some variation with time of day. And then we can sort of see the seasonal pattern here, sorry, the spatial pattern. It tends to be, it obviously seems to be a bit warmer here than on this side, and so on. So you can start to understand what these things have fitted, but it's still a relatively complex model to interpret. So we're actually going to do some things now to interpret this model better. And here is just showing what what you can get out of the draw function. It isn't as complicated, it isn't as good as plot.gam yet. It can't do those higher order things. That's why we're missing 3 of the smooths. But it does give, I think, nicer plots from ggplot. Okay, but here because I set scales equals 3, we see this is now the nonlinear pattern in the time of day. Okay, it's a bit weak actually, but there does seem to be an effect there. And actually, some of that time of day effect is actually bound up in one of these higher order terms. So let's do some predictions now, because we want to understand, we've got a complexity in this model. We want to understand features from it. And so what we're going to do is I'm going to predict for midday, and I'm going to predict for a day roughly in the middle of the year, because I'm going to look at the sort of trend or the spatial pattern, for example, right? So I'm going to look at how the spatial pattern is changing over time, over years. So I'm fixing the day of year and I'm fixing the time of day. So we can ignore those effects essentially. And then we'll look, so it's plotting for, I'm going to have it for every year, and I'm having it for a grid over the latitude and longitude, for example. Okay? And I'm excluding data points here using this exclude.toFar. I'm excluding those that lie too far away from the observed data. We don't want to extrapolate too far beyond the observations. Okay, and I just set those input data to be NA, so it just makes them be missing. Yeah, so they don't actually get plotted or set. Right. So we've predicted here, and then I'm just setting them to be NA. So when I plot them, I'm not actually showing any extrapolation. And then we use ggplot to plot this. I won't go through this, but we're going to get it as a faceted plot like this. And so we know we can start to visualize the spatiotemporal variation in the data set. And we can go one step further. We can actually animate this using the ggAnimate package. The code to do this is in the slides, but it's showing you how to animate. And so we can see quite clearly that there's this hotspot here. I don't know much about these data, but there's this hotspot here, but things start to warm up in certain areas at different, they don't warm up at the same degree here and here. So the spatial pattern is changing through time. And so by looking at a fixed day of year, we can start to evaluate that. And you could do it for a different day of year. This is just showing it in that warm summer period, for example. And then another thing that you could do now is we could look at the trends over time for some different days of year. So I fix my time of day again at 12 because that's a nuisance parameter. I'm not really worried about that one. Now I'm going to look at 3 different days of year: day 1, day 90, day 118, day 270. I'm going to look at a sequence of years, but I'm going to do it for a fixed location. So I've picked a location somewhere in Galveston Bay inside the area that we have data for, and I'm going to look at the trend. And the rest of this then is just doing the same sort of stuff, adding credible intervals and plotting as we saw before. And then this is what we get. So this is then the trend in so the January temperatures. This is the trend in the summer temperatures and so on. So with a complex model like this, you kind of have to do these sorts of interrogations. You have to predict on the response scale, but you have to hold some of the covariates fixed so that you can look at some of the other covariates. So because the long-term trend is different at every space in space. So I had to pick some spatial locations to actually visualize what that long-term trend looked like. If I want to look at the long-term trend, the only other way I could do it would be to choose a day of year and then vary the year term whilst looking at every spatial location. Okay, so you can look at different facets of the data by holding coefficients, holding some of the data fixed whilst allowing other terms in the model to vary. And there's a function in GAM called vis.gam. So there's a function in mgcv called vis.gam that will facilitate this. And there is a function in Gratia that facilitates doing some of this as well. I've shown you how to do it by hand here because knowing how to do it makes you understand what the model's doing. Once you understand these properties of how to do this stuff, then you can let the computer do it for you because it's much faster. But it's good to understand what we're doing when we're wanting to visualize these more complex models. Okay, I'm going to have a look at some of the questions. We run over a little bit, apologies for that. I'll look at the questions now and answer those. Just wanted to point out lots of extra resources. If you are into GAMs and really want to learn more, then this book by Simon Wood, it's on the 2nd edition, Generalized Additive Models, An Introduction with R. This book is great. You can ignore some of the more complexy, fancy stats sections if you want whilst you're working. And it has lots of practical advice about fitting GAMs. So it's really useful. I really recommend it if you're going to start working with mgcv. It also has lots of information that translates to fitting these models in things like JAGs or BRMS and what have you, because it actually explains what's going on in those kinds of models as well. Even though Simon doesn't use BRMS here, it still translates. I'd like to point out that my colleagues, Dave Miller, Noam Ross and Eric Peterson have given several courses at Ecological Society of America meetings. And so the latest version, I think, of those are at this repository here. So lots more material there. And some of the slides that I have here were taken from that. Big shout out to Noam Ross's GAM course. It's a free GAM course that he's put together, and is really excellent if you just want to, if you're starting to learn the basics of GAMs. Covers a lot of what I've covered here, but he does it in a course with questions and modules to go through. Doesn't cost anything. Check that out, it's great. And then a couple of papers, bit of shameful self-promotion, but if you're interested in modeling time series, especially if you're a paleoecologist, then this paper that I wrote in Frontiers in Ecology and Evolution a couple of years ago explains how to use these models to do that time series modeling with irregularly spaced data that we happen to have in paleo all the time. And the supplements, there's a supplement that includes the code to do everything in the paper is there. So all the R code explaining how I did everything. And then if you want to get more involved in GAMs, then start fitting more hierarchical models and having lots of different smooths that vary with different things. Then this paper that Eric Peterson, Dave Miller and Noam and I wrote in Piaget is sort of like a tutorial paper, which is another way to move. And then this is my blog. I have lots of stuff on there with GAMs. I don't post that often, but a lot of people do find it useful. So go and check that out because there's lots of things that I've talked about there as well. Okay, so let's have a look and see if there's some questions that I can answer while I'm still here. So model selection, can you compare GAMs to GLMs? You can do that, although you're not really comparing like with like when you're comparing a GAM that's got a smoother versus a GLM that doesn't have a smoother in. You're much better off fitting the models in GAM on its own and comparing them. So then at least you know that you've got exactly the same algorithm working on. Also, another reason for using the GAM function is that you can have more families. So it can work with more data types than just the GLM function. All right. So I would do them all in the GAM function and then use AIC or ANOVA to compare those models if you need to. Okay. So question then, when we're doing the select equals true, and in that example I showed several of those variables were identified as having no effect. Question here is saying, would I then drop those insignificant variables in the next model? I might do that. I actually think what I would probably do actually would be to leave them in there. Because whilst the estimated effects, they're close to zero, they're not exactly zero. And if I was to delete them from the model and rerun it, or to what have you, then I might be introducing bias. A, because they're not exactly zero, and I'd be saying they would be zero by dropping them out. But also the output from summary, then if you fitted that model, it wouldn't know that you had done that selection. And so you wouldn't get the same p-values, and actually the p-values would be biased, right? So really, I just leave them in there and just say that their estimated effects were essentially zero, and I leave them in. So someone's saying that they're still confused about the null space. Does it include only lines with zero slope? Okay, so if we're talking about the second derivative penalty, that's the default, the second derivative, then we're not talking about the slope of the line, we're talking about the change in that slope over time. So if I have a straight line, the slope is constant, it doesn't change, so its second derivative is zero. So therefore, for those terms, if we have the penalty is on the second derivative, it can't affect anything that's a straight line. Any straight line, the penalty can't affect those straight lines because their derivative is zero, so they don't contribute to the penalty at all. So there's no way to shrink them. So what you do in that instance is it doesn't affect just the flat functions, which actually get removed from the basis anyway because they're confounded with the intercept. We're interested about these things that could be estimated as linear functions, but really, if there's no effect, we want them to be estimated as flat ones. And we can't go from something like this to a flat function using the standard penalty. What we have to do is when we turn on select equals true, for example, it puts a penalty on that null space. So any terms that are in that null space will get penalized as well. So it'll take this thing and it can penalize it back to a flat function. Now, if you change the order of the penalty, let's say you have a penalty on the first derivative, Now the flat function has a penalty, right? This contributes to the penalty because it has a slope. So if the penalty was on the first derivative, then that could get penalized back to a flat function, okay? Or if we had like a penalty on the third order derivative, then functions that some of the null space would actually contain nonlinear functions, okay? Because they're ones that are smooth, i.e. the second derivative isn't changing much, right? Would be in there, okay? So the null space really depends on the order of the penalty, but by default, because you're using second order penalties, by default, it can't affect anything that's a straight line. And when we turn on select equals true, then we can penalize straight lines back to flat functions. Okay, marginal effects. Yeah, people are asking, what would you do for looking at sort of marginal effects of terms after you fitted the model? You're trying to interrogate the model. Well, that bit that I was just showing for Galveston Bay is a kind of marginal effect. But one package I would recommend is the EM means. I'll type that actually into the in here. So it's the EM means package. I'll put that in the Google Doc. And that works with mgcv models and can do these. They're called estimated marginal means or marginal effects. And it can do a lot of that for you. So you can sort of look at the effects of certain variables whilst holding the others at some particular values or what have you. Someone's asking, what's the best way to choose the model structure? So when I sit down and when I'm doing this, I like to think about the theory. And so I don't ever approach these models without knowing something about the background, having that domain knowledge. If you're a statistician and you're going to use these models, perhaps you don't have that domain knowledge. I think it's really important that you work with somebody who does have that domain knowledge, because what you want to try and do is you want to try and write down a model like I did for the Galveston Bay. So we can think about it, and you don't have to write it in fancy LaTeX stuff like I did here, right? You can write this down, whatever, but it's just thinking about the different terms in the model. And so, okay, might be some variation with the time of day, or there might be some variation in space. So write down the things that I think are going to vary, be it on what do I know of the properties of the data, but also what do I know about the sort of science of that area, that field. Okay, and so that's what I then use to inform what terms go into the model. Usually I try to sort of fit a general model at first, a sort of simple model. So I might fit the one that just included those first few smooth terms in there. And then I would sort of make the model more complex and see whether I need these higher order terms. Usually if I've got data collected repeatedly at the same observation, the same sampling stations or whatever, same subjects, then yeah, I think I would include a random effect automatically there. Because even if there are other terms in the model might explain variation, like here there's spatial pattern might explain variation between the stations, there still may be some random variation at individual stations that we want to account for, and the random effect would do that. How do we report the results of GAMs? Yeah, this is actually quite, and I think this is the same problem as you have with complex models in general, because even though with a general, it's like say you've got a generalized linear model, a complex generalized linear model that has lots of coefficients in it with lots of interactions, you could just present those coefficients, okay, as a table or as some graph with some confidence intervals on, for example, to see which ones were close to zero or not, included zero. So you could write that table down, but the interpretation, what do those coefficients mean in a complex model, is actually quite difficult to convey to people what those things actually mean. We can look to see whether the numbers are consistent with being zero or not, given the uncertainty, or look at the magnitudes of them and interpret them as some magnitude. Oh, these things, this looks like a big effect. But what do they actually mean scientifically is another question. So we have the same problem with the GAMs, and we want to, but at least with the GAMs we can plot the smooths. Okay, and I actually think doing a lot of plotting is really useful with GAMs, because you have a function, you can't represent it as a single parameter, so you want to show the function, so plot those functions. And so what I typically do is I would report the functions and then maybe create a bit of a table out of the summary for the smooth effects and things. But usually the best way is really to create the graphs, the plots to show what these effects are. And as we saw in the Galveston Bay example, you can't just plot a particular smooth and have it meaningful. Like that interaction between space and time, that smooth itself is not that useful as a thing, because we've got the spatial, that interaction term doesn't include the main effects. And so we might want to, as I did in the Galveston Bay example, we might want to choose some ways to visualize the model by fixing some of the terms at some known values, and then go on from there and just show what the trend might look like or what the spatial pattern is, fixing some values. Okay, so yeah, someone's asking here, when the smoother is time for time series, shouldn't we be accounting for temporal autocorrelation? Oh, well, yes and no. And this is why I didn't include this here. If I ever do a more advanced one of these over the summer, or maybe I'll do something about this particular question as a live stream or a video maybe. Yeah, you're not really violating the assumptions of the model so long as you model that autocorrelation. That's the key bit. Remember, the assumption is that the responses conditional upon the model are independent. It doesn't say that the response itself is independent. So a lot of that temporal autocorrelation or the spatial autocorrelation in the data might actually be modeled. Maybe you have a spatially smooth, the effect of space is actually relatively smooth and you can model that. Maybe the trend is smooth and you can model that easily in the GAM, leaving the residuals or the observations conditional upon the model being independent. There are a couple of problems though with time series, and I'm not going to explain this, but I will say a couple of problems in space and time. One of them is if you try to include a smoother and a correlation function, like with a GAM-M function that you can do, then there's a lack of identifiability. A very wiggly smooth can be interpreted as a correlation function with a very large autocorrelation parameter. And so what you can get is you can't, unless you inform one or the other, you put some restriction on how wiggly the smooth could be, or you put some restriction on the value of the autocorrelation parameter, there isn't information in the model to uniquely identify those two things, and then something at random will win. All right, and it will, when I mean at random, you could run the model on your computer and I could run it on my computer, and we might get entirely different answers, because you might get a wiggly trend and I might get a really complex correlation structure. So you have to be a bit careful about modeling time series and trying to put smoothers in there and trying to put temporal autocorrelations in there. Okay. So someone's asking here, what do I recommend about reporting results? Should we transform the y-axis to be the real response variable in units? So I think, in this here, it's like trying to take, because the smooths, when you plot them with plot.gam or with draw, they're all done on the scale as a link function. And I think what they're getting at here is, how do you get these things back onto the response scale so that you can show them in the real units that you're actually interested in? And in that sense, I don't think you should. I really don't think you should use the shift or the transformation, the transform argument in plot.gam, or there's equivalent functions being added to draw at the moment. I really don't think you should do that. I think if you're wanting to do that kind of thing and to show the outputs from the model, you should actually do some predictions and get the predictions on the response scale. You can always exclude the effects of all the other terms. So you could, in the Galveston Bay example, I did them conditional upon. So I created predictions conditional upon some values for time of day and space or what have you. But you can just set them to be 0 using the exclude argument to the predict method. And if you exclude them, then it's essentially just saying that they have no contribution. So you can get predictions on the right scale because they include the intercept, but you're just sort of saying, well, This is just what that smooth looks like, and that would be one way to do it. I actually think a better way to do it is actually to do what I did with Galveston Bay and try and do these conditional things where you hold some of the covariates that you don't want to vary, you hold them at some fixed values, and then you vary the other things like the space and the trend. So how would you compare two models fitted to different data? I don't think you could really compare two models. At least you can't do it sort of statistically, I don't think, for that. Because, yeah. And so if the data sets, if the reason for comparing the models is that you're trying to fit one model to some subset of the data, and then you're trying to do the same thing, the same kind of model, but to a different subset of the data, if those subsets, if it's the same kind of response, then I would maybe use like the factor bivariables or a hierarchical sort of model and try and fit one model. And then because I fitted one model and I can actually do things like look at the differences between smooths that have been fitted in one subset, like one part of the factor versus another factor level, I can actually compare things that way. Okay. I'm not 100% sure what you mean about sort of fitted to different data. So if you are still on and you want to explain that question, then just go and add something to that and I'll maybe take a look. So someone's asking about count for spatial autocorrelation in the Galveston Bay and whether that smooth of longitude and latitude, does that account for the spatial autocorrelation? Yes, it does. I mean, I think you have to be a bit careful about using, basically there's spatial structure in those data, and let's go back to it. There's spatial structure in the data, and so if we include these spatial terms like this is the spatial term, and then this is how the space one varies in time. Okay, if we're fitting these things, then we are modeling that spatial pattern, and therefore we shouldn't have any residual autocorrelation. Hopefully we won't have any residual autocorrelation in our data. Yeah, but this term is the main effect for space, but then the spatial effect, because it's changing with the time of day, the day of year, and the year, the actual spatial effect is bound up in this main effect and each of these higher order interactions. So it's not just one term where the spatial effect is being identified and accounted for. It's in multiple terms. Okay. A couple more questions were just coming in as I answered those. Okay. So again, related, someone's asking about how did I account for the spatial and temporal correlation. So a more thorough analysis of the Galveston Bay data would have looked to see if there was any residual spatial autocorrelation, any residual pattern, spatial pattern in the residuals, any residual temporal pattern left over, because then we might need to have some correlation term in here, or I might need to increase, we might need to do something else, like put in a random effect for the station, for example, to actually mop up that residual autocorrelation. So a more exact analysis would have actually tried to look at that. But if you're talking about the spatial, when you say spatial and temporal correlation, you're meaning just the spatial temporal patterns, then the model accounts for that. And so it doesn't matter that the data are not independent. What matters is whether the residuals are independent. So in that Galveston Bay model, because the data are spatial, to create a spatial plot, yeah, you would need to have lat long or some spatial coordinates to do that. You could just, a way I did it two different ways. One, I predicted for the whole grid. So I had the whole grid over Galveston. I created a grid over Galveston Bay, centered on where the data were, and then I trimmed off bits that were too far from the observations. But then in one of the other examples that we did with Galveston Bay, looking at the trends over time, I just took a fixed spatial location and looked at the trend there. But yeah, you would need to use have that spatial information to do that. So to look for residual spatial autocorrelation, yeah, you could just take the residuals and do them as a heat map, yeah, on there. Because this data is a bit complex for Galveston Bay, it's space and time, so you'd have to try and separate those two things. But yeah, that's one of the ways I would do that, yeah. Okay, so you can't, so someone's asking, what is the equivalent of the ANOVA decomposition for S of x plus S of z plus the TI interaction of x and z? What's the equivalent when z is a factor? So in that instance, that's actually the bifactor term. So I had that in my slides, and this is going to have to go way back up here. Sorry, I really need to get that overview utility added in here so that that somebody was talking about on Twitter, because it would make this a lot easier. That here, yeah. So let me just go to that. Okay, so this is the way you get an interaction. So this is the main. The one way to do that is it'd actually be slightly different from this. You'd have your main effect of the factor. You'd have to put S of x in here, and then you would have S of x by the factor. Okay, and there is one other trick that you would need to do, and we talk about that in the HGAM paper that Eric Peterson led in Piaget, which I mentioned at the end. So go and look at that. You have to set the penalty here. You have to set m equals 1 in the bifactor, because these things are they can be concurved with the main S of x, the main effect. Okay, so if I'll flick back to the thing and just sort of quickly write that in as the sort of thing here. So it would be you had f plus S of x plus S of x by equals f, m equals 1, and that would give you the equivalent if you had a factor, and that would be like a fully decomposed kind of thing. Okay. Is there a convention for a prospective power analysis? Like, I think you mean here you're talking about doing a power analysis before you collected the data. I think with anything as complex as a GAM, I'd be looking to do simulation to look at the power. I'd simulate data according to some, you'd have to approximate the sort of effects that you have in some way, but you'd have to sort of simulate some data. I don't think it's particularly easy to do that for GAMs, because if you had enough theory to say what the functional form should be, then maybe you should be fitting that model, right? And not letting the GAM decide that. But maybe you're also assuming some functional form and you want to see, can my GAM recover that functional form? Then yeah, but you would have to know that functional form to be able to do it. Okay, someone's asking a bit more about autocorrelation. Seems like I should probably do something on GAMs and time series. But yeah, if you've got regularly spaced data and you have a model for time, and you take the residuals, and you can use the autocorrelation function plot of the residuals and look at if there's any temporal structure there at these different lags, then that's a good way to diagnose the residual autocorrelation. If you've got data that are irregularly spaced in time, then you would have to use something like a variogram or something and treat time as a one-dimensional spatial process. But yeah, that's the way to go and look and see if you've got residual autocorrelation. And then you'd be looking at doing things like the GAM-M function and trying to get some temporal correlation in there. Or using BRMS, you can do the same thing. But as I said earlier, there is this lack of identifiability between these the autocorrelation and a wiggly trend. And so you have to work a lot harder to fit those models. Someone's asking about how the bifactors work. Okay. So I think I've talked about ordered factors. The ordered factor, basically, you have to set it up a bit like I just set up when someone was asking for that fully decomposed thing. So what you have to do is the ordered factor, let's say f is an ordered factor. So you include f in your model, okay? And then if you just did this as for an ordered factor f, then it would ignore the smooth for the reference level, okay? So So that would be like the first level of f. You wouldn't get a smoother for that, but you get what this would estimate would be a difference between the smooth for the reference level and each of the new levels, the other levels in the data. So you actually have to fit the smooth for the reference level. So that model you would need plus s of x in here. So you'd have like the main effect s of x, but really what that represents, because it's an ordered factor, that first s of x term, that just represents the reference level of the factor, and then these by factor terms are the smooth differences between that s of x term for the reference level and each other level. So it's exactly the same as you get if you do like ANOVA in LM or GLM. The intercept represents the reference level, and then the other coefficients, they represent the differences between the reference level and each of the other levels that you have. This is the same here. You have a reference level smooth, which would be s of x, and then these by smooths represent the smooth differences between them. Okay. I have a bit of a blog post that explains that a little bit more on my blog, so it might, if that's not clear, it might be worth having a look at that. Okay. One more question come up here. Can't see because someone's editing it. Are there reasons to use a by interaction for two continuous variables rather than a full TD? So you can't really use the by interaction to get interactions between two continuous variables. You can have a linear by thing. I didn't talk about that because that's sort of a bit more of a complex model, but the by variable can be a linear one. But what you're doing there is not doing the same thing as a tensor product. You're saying that you have a linear effect of that by variable, so there's a linear effect, and then you're saying that the coefficient for that linear effect varies smoothly as a function of whatever the smooth variable is. So let's just assume that f is, let's ignore the f here because you wouldn't need to include it. But if I did this, if x was continuous and f was continuous, then what that's saying is you have a model where you've got a linear effect, so there's a linear thing, but the actual slope of that linear line varies smoothly as a function of s. So this thing could be moving around like this as s varies. Okay? And so if you really, what you should do, I think, if you've got two continuous variables, use the tensor products and maybe put on select equals true on them or something, because that can give you, even if you don't have select equals true, that can give you a linear function that's then varying smoothly, okay? But it just doesn't force it to be linear, right? So I think just assuming that things are linear is not always a great idea, especially in applied things, partly because often we have nonlinear, often nonlinearity is the norm. And so assuming things are linear is not always a good idea. So I'd fit the tensor interaction, the TE thing, and then see what happened. It's only if I had a good reason, only if the model that I wanted to fit really was some sort of, it's called a varying coefficient model. Even if that's what it was like, then I only then would I maybe try and fit that kind of model. Someone's asking, how would one model higher order interactions with two or more factors? So let's say you want to have by variables, but you want to have you want to have a smooth for each combination of the levels of the factor. So the way that I would do that is that I would add in the factors, like you could put in f1 times f2 as parametric effects, but then what I would do before I fit the model, I would create a new factor, which was the interaction between f1 and f2, right? Or f1, f2, and f3 if you want them, okay? Because really all the bivariable thing is doing is trying to get a spline for all the levels. And so if there is an interaction between those two factors and you want a spline for each of those levels, then basically what you're doing is you want a spline for all the combinations of the levels of the two factors. So there's a function called interaction in base R, which allows you to just give it the two or more factors that you want in the interaction, and it will return a new factor that is the interaction. Okay? And then by default, it will make the levels be all possible levels, even if you don't have any data for them. So you can always add drop equals true when you do the interaction, and it would get rid of those extra levels that you didn't observe. Okay, that's how I would do that. Okay, and that really is the same, because all the bivariable thing is doing is setting up the model matrix so that you get a smooth for each combination of the factor levels. So it works just fine. But you can, I would still use F1 times F2 in the model formula to get my fixed effect values, right? So I wouldn't use this new interaction there. I think it's better to be able to interpret the coefficients, the group means, using the standard way that you would fit them if you're doing ANOVA. It's just I would use by this new factor variable if I wanted to. Okay, I'm starting to lose my voice a bit, and I need to go and look after my kids and spend some time with them. So I'll just finish. Just wanted to couple more acknowledgements, and I have to go right to the end, I think. Okay, so yeah, just a couple acknowledgements. I'm funded by NSERC. My lab is funded by NSERC. Recognize them. Actually, NSERC have been brilliant during the this COVID pandemic, where a lot of people's research has been disrupted. We've been allowed to keep on our students, and they're giving us more money to cover that, our grad students and our RAs and things. And also they're extending our grants, and I think this is great. So thanks NSERC for everything that you do, that have enabled me to do this. And there are a lot of the research that goes into some of the work behind these, understanding these GAMs and things in an applied sense. That's directly funded by my NSERC Discovery Grant. And also a big shout out to my fellow GAM workshop colleagues, Dave Miller, Eric Peterson and Noam Ross. A lot of what you saw here, bits of it anyway, were I take full responsibility, but bits of this here are taken from our workshop slides. And it's been great chatting with all of them about GAMs and how we fit them and how we use mgcv. And writing the paper together with these guys was great. So thanks to them. Slide deck is up and the sources. So if there was something in the slides that you were really interested in and I didn't show the code for it, everything is in the slide deck. So go and help yourselves. I will get the recording up as soon as I can. You can watch back the live stream, but the recording should be up soon, I think. And just a reminder that if you are financially available, I haven't been charging for this webinar. If you are able to, I'd really appreciate if you could make a donation to the U of R's Student Emergency Fund. I mentioned this earlier, but it really would be great if you could do that. So thank you very much, everybody. I hope you found the webinar interesting. If you are still on and you do have some suggestions for things that I didn't cover that you would have liked me to have covered, then stick them in the Google Doc, and I'll sort of use that as perhaps maybe do a more advanced GAM thing or tackle some other things later in the summer, or maybe in the fall as classes start. But yeah, anyway, hope you've enjoyed it, and yeah, thanks for watching. Bye-bye.